In the courtyard of the Qatul Islam Mosque in the Mehrauli district of Delhi, India, there stands an iron pillar that is approximately 7 meters tall, weighs more than 6 metric tons, and has been standing in the open air for approximately 1600 years. It has been exposed to the monsoon rains of the Indian subcontinent, to the blazing heat of the Delhi summer, to the humidity, the dust, the pollution, and the corrosive atmosphere of one of the most challenging environments on Earth for the preservation of iron, and it has not rusted. That sentence requires emphasis because it describes something that should be impossible. Iron rusts. This is one of the most fundamental facts of materials science. One of the first things that anyone who works with metals learns. One of the most costly and most persistent problems that the modern world faces. Iron, when exposed to moisture and to oxygen, the iron atoms on the surface of the metal react with the oxygen in the air and the water in the atmosphere to form iron oxide, the reddish-brown compound that we call rust. The process is relentless. It is unstoppable by any ordinary means. It destroys bridges, automobiles, ships, pipelines, buildings, and infrastructure at a cost that has been estimated at trillions of dollars worldwide each year. Modern engineers spend enormous resources attempting to slow the process, using paints, coatings, galvanization, cathodic protection, and corrosion-resistant alloys to protect iron and steel from the environment. And yet, the process continues, consuming the iron structures of the modern world at a rate that is measured in millimeters per year. The iron pillar of Delhi has been exposed to the same environment that destroys modern iron structures. It has been exposed to 16 centuries of monsoon rain, of humidity, of atmospheric oxygen, of all the chemical agents that cause iron to corrode, and yet its surface remains smooth and clean, covered not by the rough, reddish-brown crust of rust, but by a thin, uniform, dark grey film that protects the metal beneath from further corrosion. The film is approximately 1/20th of a millimeter thick, and it has been growing, slowly and steadily, for 1600 years. It is this film, this microscopically thin layer of protective material, that has preserved the pillar from the corrosion that destroys ordinary iron in a matter of years. The pillar was erected during the Gupta dynasty, one of the greatest periods of Indian history, a period that has been called the Golden Age of Indian civilization. The inscription on the pillar, which is written in Sanskrit, in the Brahmi script, attributes the pillar to a king named Chandra, who is generally identified with the Gupta Emperor Chandragupta II, who reigned from approximately 375 to 415 of the Common Era. The pillar was originally erected at a site called Vishnupadagiri, possibly at Udayagiri in central India, and it was later moved to its present location in Delhi, probably in the 11th century, when the area was developed as the site of a mosque. By the end of tonight, you are going to understand what the iron pillar of Delhi is, how it was made, why it has not rusted, and what modern science has discovered about the extraordinary chemistry that protects it from corrosion. You are going to learn about the specific composition of the iron, the specific chemical processes that formed the protective film, and the specific conditions that have allowed the pillar to survive for 16 centuries in an environment that would destroy modern iron in decades. And you are going to confront a question that has haunted metallurgists for over a century. How did the ancient Indian ironworkers produce a material that is, in one specific and critical respect, superior to the iron and the steel that the modern world produces? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The iron pillar of Delhi has stood for 1600 years without significant corrosion. Modern iron structures, built with the most advanced metallurgical techniques available, begin to corrode within months of their construction if they are not protected by coatings or other anti-corrosion measures. The ancient Indian ironworkers who forged the pillar knew something about the production of corrosion-resistant iron that the modern world has only recently begun to understand. The secret, when it was finally discovered, turned out to be simultaneously simple and profound, a solution to one of the oldest problems in metallurgy, that was achieved not through sophisticated chemistry or advanced engineering, but through the specific properties of the raw materials and the specific techniques of the ancient Indian iron-making tradition. Now, let us begin. The contrast between the pillar's survival and the fate of modern iron structures is one of the most humbling comparisons in the history of materials science. The Eiffel Tower in Paris, which is one of the most iconic iron structures in the modern world, requires the application of approximately 60 tons of paint every 7 years to protect it from corrosion. The Golden Gate Bridge in San Francisco employs a permanent team of painters who continuously repaint the bridge's surface to combat the corrosive effects of the salt air and the fog. The infrastructure of the modern world, the bridges, the pipelines, the transmission towers, and the shipping containers that sustain the global economy, is engaged in a continuous battle against corrosion that consumes billions of dollars in maintenance costs, and that requires the constant attention of engineers and maintenance workers. The Iron Pillar of Delhi has fought the same battle, alone and unaided, for 1600 years, and it is winning. The pillar's endurance is even more striking when one considers the specific environmental challenges of the Delhi climate. The temperature in Delhi ranges from approximately 5 degrees Celsius in the winter to over 45 degrees Celsius in the summer, a range that subjects the metal to thermal expansion and contraction cycles that can promote cracking and fatigue in modern metals. The humidity ranges from approximately 20% in the dry winter months to over 90% during the monsoon, a variation that ensures that the surface of the pillar is alternately wetted and dried hundreds of times each year. And the atmosphere of modern Delhi, which contains industrial pollutants, vehicle exhaust and particulate matter, is more corrosive than the atmosphere of the Gupta period would have been, meaning that the pillar has been subjected to increasingly aggressive conditions as the centuries have passed. To understand the Iron Pillar of Delhi, we must first understand the Indian iron-making tradition, which was one of the most ancient and most sophisticated metallurgical traditions in the world. The production of iron in the Indian subcontinent has a history that stretches back over 3,000 years, and the Indian ironworkers developed techniques and achieved results that were, in specific and measurable ways, superior to the iron production of any other ancient civilization. The earliest evidence of iron production in India dates to approximately 1800 to 1200 years before the Common Era, placing India among the earliest centers of iron technology in the world. The iron-producing regions of India, which included the mineral-rich areas of Karnataka, Andhra Pradesh, Tamil Nadu, Madhya Pradesh, and Jharkhand, produced iron using a variety of techniques that were adapted to the specific ores, the specific fuels, and the specific environmental conditions of each region. The diversity of the Indian iron-making tradition, which encompassed multiple ore types, multiple furnace designs, and multiple processing techniques, produced a range of iron products with a range of properties that was unmatched in the ancient world. The specific technique that produced the iron of the Delhi pillar was the bloomery process, a method of iron production in which iron ore is reduced to metallic iron in a small furnace, using charcoal as both the fuel and the reducing agent. The bloomery process, which was the primary method of iron production in the pre-modern world, produces a solid mass of iron called a bloom, which is a spongy mixture of metallic iron and slag, the non-metallic residue of the smelting process. The bloom is then repeatedly heated and hammered, a process known as forging, which squeezes out the slag and consolidates the iron into a dense, workable mass. The Indian bloomery process differed from the bloomery processes used in other parts of the world in several important respects. The Indian ironworkers used specific types of ore, specific types of fuel, and specific furnace designs that produced iron with specific chemical properties that distinguished it from the iron produced elsewhere. The most important of these chemical properties, and the one that is directly responsible for the corrosion resistance of the Delhi pillar, is the high phosphorus content of the Indian iron. Phosphorus is an element that is generally regarded as a contaminant in modern steelmaking because it makes steel brittle and reduces its mechanical properties. The modern steel industry goes to considerable effort and expense to remove phosphorus from its products, and the phosphorus content of modern structural steel is typically less than 0.05% by weight. The iron of the Delhi pillar, by contrast, contains approximately 0.25% phosphorus, a concentration that is roughly 5 times higher than the maximum allowed in modern structural steel. The high phosphorus content is a direct consequence of the specific iron ore that the Indian ironworkers used, which was a phosphorus-rich ore that transferred its phosphorus to the iron during the smelting process. The significance of the high phosphorus content for the corrosion resistance of the Delhi pillar was not recognized until the late 20th century, when modern analytical techniques were applied to the study of the pillar's iron and its protective surface film. The traditional explanation for the pillar's corrosion resistance, which had been accepted by metallurgists for decades, was that the pillar was made of an unusually pure iron that resisted corrosion because of its low content of impurities such as sulfur and carbon. This explanation, while it was partly correct, was incomplete, because it did not explain why other ancient iron objects with similarly low impurity contents did corrode, while the Delhi pillar did not. The breakthrough in the understanding of the pillar's corrosion resistance came in the late 1990s and early 2000s, when the Indian metallurgist Ramamurthy Balasubramaniam of the Indian Institute of Technology, Kanpur, conducted a series of detailed analyses of the pillar's iron and its protective surface film that revolutionized the understanding of the pillar's corrosion resistance. Balasubramaniam's research, which combined chemical analysis, microscopic examination, and electrochemical testing, demonstrated that the key to the pillar's corrosion resistance was not the purity of the iron, but the specific chemical composition of the protective film that had formed on its surface over the centuries. The protective film, which Balasubramaniam identified as a layer of iron hydrogen phosphate hydrate, a mineral compound with the chemical name misawite, was formed through a specific chemical reaction between the phosphorus in the iron on the surface, and the moisture and oxygen in the atmosphere. The phosphorus, which was present in the iron as a result of the specific ore that was used in the smelting process, reacted with the iron and the atmospheric moisture to form a thin, dense, adherent film of iron hydrogen phosphate hydrate that sealed the surface of the iron and prevented further contact between the metal and the corrosive atmosphere. The film was not applied to the surface by the ancient ironworkers. It formed spontaneously over a period of years and decades as a result of the chemical interaction between the phosphorus-rich iron and the atmosphere. The physical dimensions of the iron pillar of Delhi are themselves impressive and provide evidence of the scale of the metalworking enterprise that produced it. The pillar stands approximately 7.21 meters above the ground, with an additional portion, approximately 1 meter, buried below ground level. The diameter of the pillar varies from approximately 42 centimeters at the base to approximately 30 centimeters at the top, and the pillar tapers slightly from bottom to top, giving it a graceful, elongated form. The total weight of the pillar has been estimated at approximately 6.5 metric tons, making it one of the largest forged iron objects in the ancient world. The production of a 6.5-ton iron pillar using the bloomery process would have been a monumental undertaking. The bloomery process produces iron in small quantities, typically a few kilograms per smelt, and the production of a pillar weighing several tons would have required dozens or hundreds of individual smelts, each producing a bloom of iron that would then need to be forged, consolidated, and welded together with the other blooms to build up the mass of the pillar. The forge welding of multiple blooms into a single coherent mass is a demanding operation that requires precise control of the temperature and the timing of the welding, and the achievement of a pillar-sized weldment with a structural integrity to stand for 16 centuries is evidence of a level of ironworking skill that is extraordinary by any standard. The inscription on the pillar, which is engraved in 6 lines of Sanskrit text in the Brahmi script, provides important historical information about the pillar and its origins. The inscription praises the military achievements of a king named Chandra and describes the erection of the pillar as a standard of the god Vishnu on a hill called Vishnupadagiri. The identification of King Chandra with the Gupta Emperor Chandragupta II is based on the style of the inscription, the specific titles and epithets used, and the historical context of the Gupta period, which was one of the most powerful and most culturally accomplished periods in Indian history. The Gupta period, which is generally dated from approximately 320 to 550 of the Common Era, was a time of extraordinary cultural achievement in India. The Gupta emperors patronized the arts, the sciences, and the religions of India, and their reign produced some of the greatest achievements of Indian civilization, including the decimal number system, the concept of zero, the Sanskrit literature of Kalidasa, the astronomical works of Aryabhata, and the cave paintings of Ajanta. The Iron Pillar of Delhi is one of the technological achievements of the Gupta period, and it stands as evidence that the Gupta era's excellence extended to the practical arts of metallurgy and engineering, as well as to the theoretical arts of mathematics and literature. The Indian iron-making tradition, of which the Delhi Pillar is the most famous product, was not limited to the production of large-scale objects like pillars and beams. The Indian ironworkers also produced high-quality steel, including the crucible steel known as woots, that was used to produce the legendary Damascus steel blades that we have discussed in a previous episode. The connection between the Indian iron tradition and the Damascus steel tradition underscores the importance of Indian metallurgy in the broader history of materials technology, and it demonstrates that the Indian ironworkers possessed a body of metallurgical knowledge that was among the most advanced in the ancient world. The scale of the ancient Indian iron industry can be appreciated from the archaeological evidence of iron smelting sites that have been found across the subcontinent. The remains of ancient bloomery furnaces, the slag heaps that accumulated at the smelting sites, and the iron tools, weapons, and other objects that have been recovered from archaeological sites all provide evidence of an iron industry that operated on a significant scale, and that produced iron of high quality for both domestic use and export. The export of Indian iron and steel, particularly the woots ingots that were the raw material for Damascus steel, was a major component of the Indian Ocean trade network and was one of the most important Indian contributions to the material culture of the medieval world. The tradition of erecting iron pillars and iron beams as architectural and devotional objects was not unique to the Delhi Pillar. Several other large iron objects from ancient India have survived, including the iron beams of the Sun Temple at Konarak in Odisha, which date to the 13th century, and several other iron pillars and columns that have been found at sites across India. These surviving iron objects demonstrate that the production of large-scale iron structures was a recognized and a practiced art in ancient India, and they provide comparative evidence for the techniques and the materials that were used in the production of the Delhi Pillar. The broader context of ancient Indian civilization provides essential background for understanding the technological achievement represented by the Delhi Pillar. India in the Gupta period was one of the most advanced civilizations in the world, with achievements in mathematics, astronomy, medicine, philosophy, literature, and the arts that rank among the highest accomplishments of any civilization in human history. The Gupta mathematicians developed the decimal number system and the concept of zero, innovations that are among the most important intellectual achievements of all time, and that form the foundation of modern mathematics. The Gupta astronomers, including Aryabhata, who proposed that the Earth rotated on its axis, and who developed sophisticated mathematical methods for calculating the positions of the celestial bodies, produced astronomical knowledge that was in many respects comparable to the best available in the contemporary Roman or Persian worlds. The Gupta physicians developed medical knowledge and surgical techniques that were documented in the comprehensive medical treatises of the period. The Gupta sculptors and architects produced works of art and architecture that are among the finest in the Indian tradition, and that are celebrated for their beauty, their sophistication, and their technical virtuosity. The Iron Pillar of Delhi is a product of this extraordinarily creative and sophisticated civilization, and it stands as evidence that the Gupta era's achievements extended to the practical arts of metallurgy and engineering, as well as to the theoretical arts of mathematics and astronomy. The production of a corrosion-resistant iron pillar weighing 6.5 metric tons is a technological achievement that is consistent with the broader pattern of excellence that characterized the Gupta period, and it demonstrates that the Indian civilization of the 4th and 5th centuries was operating at the highest levels of technological capability in multiple domains simultaneously. The specific geological conditions of the Indian subcontinent played a crucial role in the development of the Indian iron tradition. India possesses some of the richest and most diverse mineral deposits in the world, including iron ore deposits of varying compositions that are found in many parts of the subcontinent. The specific iron ores that were used by the Indian ironworkers, particularly the ores from the regions of Madhya Pradesh, Karnataka, and Andhra Pradesh, had specific chemical compositions that influenced the properties of the iron that was produced from them. The phosphorus-rich ores that were used to produce the iron of the Delhi pillar were found in specific geological formations, and the iron workers who used these ores were, in a sense, the beneficiaries of the specific geological history of the Indian subcontinent, which had produced ore deposits with the specific chemical compositions that were needed for the production of corrosion-resistant iron. The charcoal that was used as the fuel and the reducing agent in the Indian bloomery process was another factor that influenced the properties of the iron. The Indian ironworkers used charcoal produced from specific types of wood, and the specific chemical properties of the charcoal, including its phosphorus content and its ash composition, influenced the final composition of the iron. The selection of the appropriate wood for charcoal production was an important aspect of the ironworker's skill, and the accumulated knowledge of which woods produced the best charcoal for iron smelting was part of the body of empirical knowledge that was transmitted through the apprenticeship system of the Indian iron trade. The furnace designs that were used by the ancient Indian ironworkers have been studied through the archaeological excavation of iron smelting sites and through the ethnographic observation of traditional ironworkers who continue to practice the bloomery process in some parts of India. The archaeological evidence reveals a variety of furnace designs, from simple pit furnaces to more elaborate above-ground structures, with specialized tuyeres, the nozzles through which air was blown into the furnace to raise the temperature. The specific design of the furnace influenced the temperature that could be achieved, the reducing conditions within the furnace, and the degree to which the phosphorus in the ore was transferred to the iron, all factors that affected the quality and the properties of the resulting iron. The air supply to the furnace, which was provided by bellows or by natural draft, was another critical variable that the ironworkers had to control. The amount of air that was blown into the furnace determined the temperature, the reducing conditions, and the rate of the smelting reaction, and the control of the air supply was one of the most important skills that the ironworker needed to master. The Indian ironworkers developed bellows designs that were specifically adapted to the requirements of their furnaces and their ores, and the efficiency of their bellows systems was one of the factors that enabled them to produce iron of high quality. The social organization of the Indian iron trade was another factor that influenced the development and the preservation of the metallurgical knowledge that produced the Delhi pillar. The Indian iron trade was organized along caste lines, with specific castes being responsible for the mining of ore, the production of charcoal, the smelting of iron, and the forging of the finished products. The transmission of metallurgical knowledge within these caste groups was governed by strict rules of secrecy and of hereditary succession, with the knowledge of specific techniques being passed from father to son within the iron-working castes, and with outsiders being excluded from access to the specialized knowledge of the trade. The caste-based organization of the Indian iron trade had both advantages and disadvantages for the preservation of metallurgical knowledge. The advantage was that the knowledge was transmitted with great fidelity within the caste group because the hereditary succession ensured a continuous chain of transmission from one generation to the next, and the rules of secrecy ensured that the knowledge was not diluted or corrupted by contact with outsiders. The disadvantage was that the knowledge was vulnerable to loss if the caste group declined in numbers or was disrupted by social or economic changes, because the knowledge was confined to a small group of practitioners and was not recorded in any written form that could be consulted by outsiders. The decline of the traditional Indian iron industry, which occurred gradually over the course of the colonial and the post-colonial periods, was accompanied by the loss of much of the specialized knowledge that had been accumulated over millennia of ironworking practice. The introduction of modern Western steelmaking techniques, particularly the blast furnace and the Bessemer process, in the 19th and 20th centuries displaced the traditional bloomery-based iron industry, and the ironworking castes that had maintained the traditional knowledge were forced to find other occupations as the demand for their products declined. The loss of the traditional knowledge, while it was not as dramatic or as sudden as the loss of some of the other ancient technologies that we have discussed, was nonetheless a significant loss because the specific techniques, the specific recipes, and the specific knowledge of ore selection and furnace management that the traditional ironworkers possessed were not recorded in written form and were not transmitted to the modern metallurgical tradition. The documentation of the surviving traditional ironworking practices in India has been an important project of ethnographers and historians of technology who have recognized the urgency of recording the knowledge of the last practitioners of the traditional bloomery process before they die. The documentation efforts, which have included the filming of traditional smelting operations, the interviewing of elderly ironworkers, and the chemical analysis of the ores, the charcoals, and the irons produced by the traditional process, have produced a valuable record of the techniques and the materials that were used by the Indian ironworkers, a record that provides insights into the practices that may have been used to produce the iron of the Delhi pillar. The specific ore processing techniques that the Indian ironworkers used before the smelting process were an important factor in the quality of the final product. The ores were typically crushed and sorted by hand, with the ironworkers selecting the pieces of ore that they judged to be of the highest quality based on their color, their texture, and their weight. The crushing and sorting of the ore removed some of the gangue, the non-metallic mineral matter that accompanies the ore, and concentrated the iron-rich portions, improving the efficiency of the smelting process and producing a cleaner bloom with fewer impurities. The roasting of the ore, a process in which the crushed ore was heated in a furnace to a temperature below the smelting temperature, was another pre-processing step that was used by some Indian ironworkers. The roasting process removed moisture, decomposed carbonates, and oxidized sulfides, improving the physical and the chemical properties of the ore for smelting. The specific conditions of the roasting process, including the temperature, the duration, and the atmosphere, influenced the final composition of the iron, and the control of these conditions was an important part of the ironworker's skill. The forging process that was used to consolidate the blooms and to shape them into the form of the pillar involved repeated cycles of heating and hammering that served multiple purposes. The hammering expelled the slag that was trapped in the bloom, consolidating the iron into a dense, homogeneous mass. The heating and the hammering also distributed the phosphorus throughout the iron, ensuring the uniform distribution that is essential for the formation of a continuous, uniform protective film. And the repeated heating and cooling cycles that were part of the forging process may have promoted the formation of specific microstructural features that contributed to the pillar's properties. The scale of the forging operation that was required to produce the Delhi pillar was enormous by the standards of the ancient world. The consolidation of 6.5 tons of bloomery iron into a single coherent pillar required the application of enormous amounts of mechanical energy, delivered through thousands of hammer blows over a period of weeks or months. The energy for the forging was provided by the muscle power of the ironworkers and possibly by the use of trip hammers, mechanical hammers that were powered by water wheels or by animal power, and that could deliver more powerful blows than human muscles alone. The use of flux during the forge welding process was an important technique that promoted the quality of the welds. The flux, which was typically sand, borax, or a mixture of the two, was applied to the surfaces of the blooms before they were heated and hammered together. The flux melted at the welding temperature and flowed between the surfaces, dissolving the oxide scale that would otherwise prevent the surfaces from bonding and creating a clean, oxide-free interface that allowed the iron atoms at the two surfaces to bond together. The selection of the appropriate flux and the control of the amount of flux used were important aspects of the ironworker's skill that directly influenced the quality of the welds. The finishing of the pillar's surface after the forging was completed involved grinding and polishing operations that produced the smooth, uniform surface that is visible today. The surface finish was important, not only for aesthetic reasons, but also for the development of the protective film, because a smooth surface promotes the formation of a uniform, adherent film, while a rough surface, with its greater surface area and its greater number of surface defects, promotes the formation of a less uniform and less adherent film. The movement of the pillar from its original location to its present site in Delhi would have required the pillar to be transported over a distance of approximately 600 kilometers through terrain that included rivers, hills, and plains. The transportation of a 7-meter, 6.5-ton iron column over such a distance using pre-modern technology would have been a major logistical challenge, requiring the construction of specialized transport equipment, the preparation of the road surface, and the organization of the labor force that would be needed to move the pillar. The successful transportation of the pillar, without damage to the metal or to the inscription, is evidence of the organizational and the engineering capabilities of the rulers who ordered the move. The relationship between the Indian iron trade and the broader Indian Ocean trading system provides an important economic context for understanding the scale and the significance of the Indian iron industry. The export of Indian iron and steel products, particularly the Wootz ingots that were the raw material for Damascus steel, was a major component of the Indian Ocean trade, and the demand for Indian iron products from the metalworking centers of the Middle East, Central Asia, and Southeast Asia was one of the driving forces of the Indian iron industry throughout the medieval period. The specific role of iron in the economy of the Gupta period, the period in which the Delhi pillar was produced, has been investigated by economic historians who have studied the Gupta coinage, the Gupta inscriptions, and the archaeological evidence of industrial activity from the Gupta period. The evidence suggests that the iron industry was one of the most important industrial sectors of the Gupta economy, providing iron tools and weapons for agriculture, for construction, and for the military, and generating revenue through the taxation of iron production and trade. The specific techniques of the Gupta period ironworkers, while they are not documented in the surviving written sources, can be inferred from the analysis of the iron objects that they produced, and from the comparison of these objects with the iron produced by later traditional ironworkers whose techniques have been documented by ethnographers. The consistency of the Indian bloomery process over many centuries, as evidenced by the similarity of the iron produced at different periods and at different locations across the subcontinent, suggests that the techniques were transmitted with considerable fidelity through the caste-based apprenticeship system, and that the specific knowledge of ore selection, furnace management, and forging technique that was needed to produce high-quality iron was maintained over many generations. The question of whether the Gupta period ironworkers recognized the relationship between specific ores and specific properties of the resulting iron is one that has been considered by researchers. The ironworkers would have had the opportunity to observe that iron produced from certain ores was more durable than iron produced from other ores, and they might have selected specific ores for specific purposes based on these observations. The selection of phosphorus-rich ores for the production of outdoor structures, such as pillars and standards, which would benefit from enhanced corrosion resistance, would have been a rational and practical decision that would not have required any understanding of the chemistry of phosphorus or of the mechanism of corrosion protection. The possibility that the ironworkers made this selection based on their empirical observations of the relative durability of iron produced from different ores cannot be confirmed or denied from the available evidence, but it is a plausible hypothesis that deserves consideration. The question of how the ancient Indian ironworkers acquired and maintained the knowledge that was needed to produce iron of the quality found in the Delhi pillar is one that connects to the broader history of knowledge transmission in the Indian subcontinent. The Indian tradition of knowledge transmission, which was based on the oral transmission of specialized knowledge within specific caste groups, was one of the most effective systems of knowledge preservation in the ancient world. The specific knowledge of ore selection, furnace design, smelting technique, and forging practice that was needed to produce high-quality iron was transmitted from father to son within the iron-working castes, and the fidelity of this transmission, maintained over many generations, ensured the continuity of the metallurgical tradition over millennia. The guild-like organization of the Indian craft traditions, in which specific crafts were practiced by specific caste groups, and in which the knowledge of the craft was the property of the caste, provided a social framework that supported the transmission and the preservation of specialized technical knowledge. The ironworking castes, which were part of the broader system of hereditary occupational specialization that characterized Indian society, had a strong economic incentive to maintain and to improve their technical knowledge because the quality of their products determined their economic success and their social standing within the community. The religious dimension of the Indian metallurgical tradition is also relevant to the understanding of the Delhi pillar. The production of iron in ancient India was often accompanied by rituals and prayers that expressed the ironworkers' belief that the quality of the iron was influenced by spiritual as well as material factors. The specific rituals that accompanied the smelting and the forging of iron varied from one region to another and from one caste to another, but they typically involved invocations to specific deities, offerings of food and other substances, and the observance of specific taboos and restrictions that were believed to ensure the success of the metallurgical process. The integration of religious practice with metallurgical practice in the Indian tradition reflects a world view in which the boundaries between the natural and the supernatural, between the material and the spiritual, were more fluid than the modern secular worldview typically allows. The environmental impact of the ancient Indian iron industry was significant, particularly in terms of the deforestation that resulted from the production of the large quantities of charcoal that were needed for the smelting and the forging of iron. The production of 6.5 tons of iron for the Delhi pillar alone would have required the consumption of approximately 26 tons of charcoal, which would have been produced from approximately 130 tons of wood. The cumulative impact of iron production across the Indian subcontinent, sustained over many centuries, would have been substantial, contributing to the deforestation of the iron-producing regions and to the ecological changes that accompanied the expansion of agriculture and the growth of population in these areas. The question of whether the environmental impact of the iron industry was recognized by the ancient Indian authorities, and whether any measures were taken to mitigate it, is one that has been addressed by environmental historians who have studied the land use practices of the ancient Indian civilizations. The evidence suggests that the Indian rulers and the Indian communities were aware of the impact of deforestation on the local environment, and that they took measures, including the regulation of forest access and the protection of specific forest areas, to mitigate the effects of the demand for wood and charcoal. The sustainability of the Indian iron industry, which operated continuously for several millennia without exhausting its resource base, is evidence that the Indian ironworkers and the Indian authorities managed the relationship between the industry and the environment with a degree of success that is impressive by any standard. The core problem with the iron pillar of Delhi is not the pillar itself. The pillar is magnificent, an extraordinary achievement of ancient metalworking that deserves admiration on its own terms. The core problem is the corrosion, or rather, the absence of corrosion, The pillar has been standing in the open air for approximately 1600 years, exposed to one of the most corrosive atmospheric environments in the world, and it has not rusted in any significant way. This fact, which seems simple to state, has profound implications for our understanding of ancient metallurgy, of corrosion science, and of the relationship between empirical craft knowledge and modern scientific understanding. The chemistry of iron corrosion is well understood by modern science. When iron is exposed to moisture and oxygen, a series of electrochemical reactions occur on the surface of the metal that convert the metallic iron into iron oxides and iron hydroxides, the compounds that constitute rust. The process begins when a thin film of water forms on the surface of the iron, either from rain, from humidity, or from condensation. The water dissolves oxygen from the atmosphere, creating an electrolyte that allows electrochemical reactions to occur on the surface of the metal. The iron atoms at the surface are oxidized, losing electrons and dissolving into the water as iron ions. The electrons that are released by the oxidation of the iron flow through the metal to another location on the surface, where they combine with water and dissolved oxygen to form hydroxide ions. The iron ions and the hydroxide ions react to form iron hydroxide, which subsequently decomposes to form iron oxide, the reddish-brown compound that is rust. The rate at which iron corrodes depends on a number of factors, including the humidity of the atmosphere, the presence of dissolved salts or acidic pollutants in the water, the temperature, and the specific composition of the iron. In a tropical environment like Delhi, where the humidity is high during the monsoon season, and where the temperature promotes the rate of chemical reactions, the corrosion rate of ordinary iron is typically in the range of 50 to 100 micrometers per year. At this rate, an iron pillar would lose a millimeter of its surface every 10 to 20 years, and over a period of 1600 years, the pillar would lose approximately 80 to 160 millimeters of its surface, a significant fraction of its original diameter. But here is the problem. The iron pillar of Delhi has lost virtually none of its surface over 1600 years. The inscription on the pillar, which was engraved at the time of the pillar's erection, is still clearly legible, with the letters sharp and well defined, showing none of the erosion or the pitting that would be expected if the pillar had been subjected to significant corrosion. The surface of the pillar is smooth and uniform, covered by the thin, dark grey protective film that Balasubramaniam identified as iron hydrogen phosphate hydrate. The film is approximately 50 micrometers thick, roughly 1/20th of a millimeter, and it has been growing at an average rate of approximately 3/100ths of a micrometer per year, a rate that is negligibly slow compared to the corrosion rate of ordinary iron. The comparison between the corrosion rate of ordinary iron and the corrosion rate of the Delhi pillar is striking. Ordinary iron in the Delhi climate corrodes at a rate of approximately 50 to 100 micrometers per year. The Delhi pillar's protective film grows at a rate of approximately 3/100ths of a micrometer per year. The ratio between these two rates is approximately 1500 to 3000 to 1, meaning that ordinary iron corrodes approximately 1500 to 3000 times faster than the Delhi pillar in the same environment. The difference is not a small, marginal improvement. It is a difference of several orders of magnitude, a difference that is comparable to the difference between the speed of a person walking and the speed of a commercial jet aircraft. The discovery of the mechanism that protects the pillar from corrosion was the result of decades of scientific investigation that began in the 19th century, when British colonial officials first drew the attention of the European scientific community to the pillar's unusual corrosion resistance. The early investigations, which were conducted in the late 19th and early 20th centuries, focused on the chemical composition of the pillar's iron, which was found to be an unusually pure iron with a low content of carbon, sulfur, and other impurities that typically promote corrosion. The early researchers concluded that the pillar's corrosion resistance was due to the purity of the iron, a conclusion that was reasonable given the limited analytical techniques available at the time, but that was ultimately shown to be incomplete. The limitation of the purity hypothesis was that it could not explain why the Delhi pillar was so much more corrosion resistant than other ancient iron objects that had similarly low impurity contents. Many ancient iron objects, produced by the same bloomery process that was used to produce the Delhi pillar's iron, have corroded extensively over the centuries, despite having compositions that are similar to the Delhi pillar's composition in terms of carbon, sulfur, and manganese content. The purity of the iron, while it may have contributed to the pillar's corrosion resistance, was clearly not the whole explanation. And it gets worse for the simple purity hypothesis. The analysis of the pillar's iron revealed that it contained a number of impurities that would normally be expected to promote corrosion, rather than to prevent it. In addition to the high phosphorus content that we have already discussed, the pillar's iron contains inclusions of slag, particles of unreduced ore, and other non-metallic inclusions that are typical of bloomery iron, and that would normally be expected to create sites of preferential corrosion on the surface of the metal. The presence of these inclusions, which are a normal feature of bloomery iron and which are not present in modern steel, would be expected to reduce the corrosion resistance of the iron rather than to enhance it. The fact that the pillar has survived despite the presence of these inclusions is further evidence that some other factor, beyond the simple purity of the iron, is responsible for the pillar's extraordinary corrosion resistance. The research of Balasubramaniam, which was published in a series of papers beginning in the late 1990s, identified the missing factor, the phosphorus. Balasubramaniam's analysis of the protective film on the pillar's surface showed that the film was not ordinary rust, not the iron oxide that forms on corroding iron, but a compound of iron, phosphorus, hydrogen, and oxygen, specifically iron hydrogen phosphate hydrate, the mineral known as misawite. The misawite film was dense, adherent, and impermeable, forming a continuous barrier between the iron surface and the atmosphere that prevented the moisture and the oxygen from reaching the metal, and that thereby halted the corrosion process. The formation of the misawite film was a direct consequence of the high phosphorus content of the iron. The phosphorus, which was uniformly distributed throughout the iron as a result of the specific ore and the specific smelting conditions that were used, migrated to the surface of the iron as the initial stages of corrosion began, reacting with the iron oxide and the atmospheric moisture to form the iron hydrogen phosphate hydrate compound. The compound, once formed, sealed the surface of the iron, preventing further corrosion and initiating a process of self-healing in which any damage to the film was repaired by the continued migration of phosphorus from the bulk iron to the surface. The self-healing property of the misawite film is one of its most remarkable features, because it ensures that the protection is maintained even if the film is scratched, chipped, or otherwise damaged. When the film is damaged, fresh iron is exposed to the atmosphere, and the corrosion process begins again at the damaged site. But the phosphorus in the iron migrates to the newly exposed surface, reacting with the iron oxide and the moisture to form new misawite that seals the damage and restores the protective barrier. The self-healing process is continuous and automatic, requiring no human intervention, and it ensures that the protection provided by the misawite film is maintained indefinitely, for as long as the phosphorus in the iron continues to supply the material for the formation of new film. The parallel between the self-healing mechanism of the Delhi pillar and the self-healing mechanism of Roman concrete, which we discussed in a previous episode, is worth noting. Both materials possess built-in self-healing mechanisms that automatically repair damage to the protective surface and that ensure the long-term durability of the material. In Roman concrete, the self-healing mechanism involves the dissolution of lime clasts and the formation of new cementitious material that fills cracks. In the Delhi pillar, the self-healing mechanism involves the migration of phosphorus to the surface and the formation of new misawite that seals damage to the protective film. Both mechanisms operate without human intervention. Both are sustained by specific chemical components within the material itself, and both have maintained the integrity of their respective materials for approximately 2,000 years. The role of the Delhi climate in the formation of the protective film has been an important aspect of Balasubramaniam's research. The climate of Delhi, which is characterized by a cycle of wet monsoon seasons and dry winter seasons, is particularly favorable for the formation of the misawite film because the alternating wet and dry conditions promote the specific chemical reactions that form the protective compound. During the wet season, moisture on the surface of the pillar dissolves the iron phosphate that has formed during the previous dry season, creating a solution of dissolved ions that reacts with the iron surface to form new misawite. During the dry season, the moisture evaporates and the misawite crystallizes on the surface, forming a dense, coherent film that resists further dissolution during the next wet season. The cyclic nature of the film formation process, which involves the alternation of dissolution and crystallization over the course of the annual climatic cycle, has been shown by Balasubramaniam to be a key factor in the development of the dense, impermeable film that protects the pillar. The film does not form in a single, continuous process. It forms through hundreds of annual cycles of dissolution and crystallization, each cycle adding a thin layer of misawite to the film, and each cycle producing a denser and more impermeable barrier. The process is slow, requiring centuries to produce a film of significant thickness, but the result is a film of extraordinary quality, a film that is denser, more adherent, and more impermeable than any film that could be produced by a single deposition event. But here is what makes this truly terrifying. The ancient Indian ironworkers who produced the Delhi pillar did not know about phosphorus. They did not know about misawite. They did not know about the electrochemistry of corrosion or the chemistry of passive film formation. They did not deliberately add phosphorus to their iron to promote the formation of a corrosion-resistant film. The phosphorus was present in the iron because it was present in the ore, and the specific ore that the Indian ironworkers used was a phosphorus-rich ore that transferred its phosphorus to the iron during the smelting process. The corrosion resistance of the Delhi pillar was therefore not a deliberate achievement of the ancient ironworkers. It was an accidental consequence of the specific raw materials that they used, a consequence that they could not have understood or predicted, and that the modern world did not explain until 16 centuries later. The investigation of the specific role of climate in the formation of the protective film on the Delhi pillar has been one of the most innovative aspects of Balasubramaniam's research. The climate of Delhi, which is classified as a semi-arid subtropical climate with a pronounced monsoon season, is characterized by extreme seasonal variation in temperature and humidity. The summer monsoon season, which typically lasts from June to September, brings heavy rainfall and high humidity, while the winter season, from October to March, is dry and relatively cool. The annual cycle of wet and dry conditions, with the humidity varying from approximately 20% in the winter to over 90% during the monsoon, provides the specific environmental conditions that are needed for the formation of the protective misawite film. The mechanism by which the cyclic wet-dry exposure promotes the formation of the protective film has been elucidated by Balasubramaniam through a combination of field observations and laboratory experiments. During the wet season, moisture condenses on the surface of the pillar, dissolving the iron and the phosphorus at the surface, and creating a thin layer of electrolyte in which the electrochemical reactions that form the film can occur. The phosphorus in the iron reacts with the iron ions and the water to form iron hydrogen phosphate hydrate, which precipitates on the surface as a thin layer of the protective compound. During the dry season, the moisture evaporates and the precipitated compound crystallizes and densifies, forming a compact adherent film that is resistant to dissolution during the next wet season. The alternation of dissolution and crystallization over hundreds and thousands of annual cycles produces a film that is progressively denser, more compact, and more impermeable with each cycle. The early cycles produce a film that is relatively porous and relatively permeable, allowing some moisture and oxygen to reach the underlying iron surface. The later cycles fill the pores and seal the gaps in the film, producing a progressively more effective barrier that reduces the rate of corrosion to negligible levels. The time required for the film to develop its maximum protective capability has been estimated by Balasubramaniam at approximately 300 to 400 years, a period during which the film transitions from a porous, partially protective state to a dense, fully protective state. The dependence of the film formation process on the specific climatic conditions of Delhi raises the question of whether the pillar would have been equally well preserved if it had been located in a different climate. Balasubramaniam has investigated this question by conducting accelerated corrosion tests on phosphorus-rich iron in simulated climates of varying humidity and temperature, and his results suggest that the cyclic wet-dry exposure is indeed essential for the formation of the protective film. In a continuously wet climate, the phosphorus dissolves continuously without having the opportunity to crystallize and to form a dense film, and in a continuously dry climate, the moisture that is needed to initiate the phosphorus reactions is not available. The specific climatic conditions of Delhi, with their pronounced alternation between wet and dry seasons, are among the most favorable conditions for the formation of the protective film, and the pillar's survival may partly be a consequence of its specific geographical location as well as of its specific chemical composition. The comparison between the Delhi pillar and other iron objects that have been exposed to different climatic conditions provides additional evidence for the importance of climate in the corrosion, resistance of phosphorus-rich iron. Iron objects from coastal regions where the humidity is continuously high and where the air contains dissolved salt show significantly more corrosion than inland objects, even when the iron has a similarly high phosphorus content. Iron objects from arid regions where the humidity is continuously low, show less corrosion than objects from humid regions, but they do not develop the dense, protective film that characterizes the Delhi pillar, because the dry conditions do not promote the phosphorus reactions that form the film. The Delhi pillar's corrosion resistance is therefore the product of a specific convergence of chemical and climatic factors, the phosphorus in the iron, and the cyclic wet-dry climate of Delhi, that together produce the conditions for the formation of the protective film. The detailed chemical analysis of the protective film on the Delhi pillar has been conducted using a battery of modern analytical techniques that have provided information about the composition, the structure, and the properties of the film at multiple scales. The X-ray diffraction analysis of the film has identified the primary crystalline phase as iron hydrogen phosphate hydrate, with smaller quantities of iron oxide and iron oxyhydroxide. The Fourier transform infrared spectroscopy analysis has confirmed the presence of phosphate groups and hydroxide groups in the film, consistent with the identification of the primary phase as iron hydrogen phosphate hydrate. The Mossbauer spectroscopy analysis, which provides information about the oxidation state and the local chemical environment of the iron atoms in the film, has revealed that the iron in the film is in the ferric state, the oxidized form of iron, consistent with the formation of the film through the oxidation of the iron surface. The scanning electron microscopy examination of cross-sections of the film has revealed its layered structure with distinct layers that correspond to the annual cycles of wetting and drying that the pillar has experienced. The individual layers, which are typically a few tenths of a micrometer thick, can be counted like the rings of a tree, and the number of layers provides an estimate of the age of the film and of the rate at which it has been growing. The counting of the layers in the film has confirmed that the film has been growing for approximately 1600 years, consistent with the known age of the pillar. The adherence of the film to the underlying iron surface has been measured using scratch testing and pull-off testing, techniques that measure the force required to detach the film from the surface. The results of these tests have shown that the film is extremely well adhered to the iron, with adhesion values that are comparable to those of modern corrosion-resistant coatings. The strong adhesion of the film is one of its most important properties, because a film that is not well adhered to the surface can be easily removed by mechanical action, such as windborne particles or flowing water, exposing the underlying iron to corrosion. The porosity of the film, which determines its effectiveness as a barrier to the penetration of moisture and oxygen, has been measured using electrochemical impedance spectroscopy, a technique that measures the electrical impedance of the film as a function of the frequency of an applied electrical signal. The results have shown that the film has very low porosity, consistent with its effectiveness as a corrosion barrier. The low porosity of the film is a consequence of the cyclic formation process, which produces a progressively denser film with each cycle of wetting and drying, filling the pores and the defects that are present in the earlier stages of the film's development. The question of how the protective film interacts with the pollution in the modern Delhi atmosphere has been investigated by researchers who have analysed the outermost layers of the film for the presence of pollutant species, such as sulfate and nitrate ions, that are characteristic of the industrial and vehicular pollution in modern urban environments. The analysis has revealed that the outermost layers of the film do contain traces of pollutant species, but that these species have not penetrated into the deeper layers of the film and have not compromised the film's protective capability. The film appears to be resistant to the corrosive effects of modern atmospheric pollution, a finding that is consistent with the continued preservation of the pillar despite the increasing pollution of the Delhi atmosphere over the past century. The broader implications of the Delhi pillar's corrosion resistance for the understanding of atmospheric corrosion have been explored by corrosion scientists who have used the pillar as a natural laboratory for the study of long-term corrosion processes. The pillar provides a unique opportunity to study the behavior of iron over timescales that are far longer than any laboratory experiment can replicate, and the information that has been obtained from the study of the pillar has contributed to the development of improved models of atmospheric corrosion that are used in the design and the maintenance of modern iron and steel structures. The study of the Delhi pillar has revealed that the process of atmospheric corrosion is more complex and more variable than the simple models that are used in engineering practice suggest. The formation of the protective film on the pillar is not a simple one-step process, but a complex multi-stage process that involves the initial formation of a porous, partially protective layer, the gradual densification and sealing of this layer over decades and centuries, and the eventual development of a fully protective film that reduces the rate of corrosion to negligible levels. The understanding of this multi-stage process has important implications for the prediction of the long-term performance of modern iron and steel structures, because it suggests that the early stages of corrosion, which are typically used to predict the long-term corrosion rate, may not be representative of the long-term behavior of the material. The study of the Delhi pillar has also revealed the importance of the specific chemical composition of the iron in determining the character and the effectiveness of the protective film. The presence of phosphorus in the iron, which promotes the formation of the dense, impermeable misawite film, is a compositional factor that is not typically considered in the design of modern structural steels, which are formulated to minimize the phosphorus content for reasons of mechanical property rather than corrosion resistance. The recognition that the phosphorus content can have a beneficial effect on the corrosion resistance of iron, a recognition that was made possible by the study of the Delhi pillar, has led to a re-evaluation of the role of phosphorus in the atmospheric corrosion of iron, and to the consideration of phosphorus-containing steels for specific applications where corrosion resistance is more important than maximum ductility. The investigation of the relationship between the microstructure of the iron and the morphology of the protective film has been another productive area of research. The slag inclusions in the pillar's iron, which are a normal feature of bloomery iron, create local variations in the chemistry and the microstructure of the iron's surface that influence the formation and the structure of the protective film. The analysis of the film in the vicinity of the slag inclusions has revealed that the film is thicker and more complex in these areas, reflecting the local chemical differences between the slag and the iron. The influence of the slag inclusions on the film formation is an important consideration for the development of modern phosphorus-containing steels, because the slag inclusions, which are not present in modern steels, may play a role in the formation of the protective film that is not replicated in the cleaner, more homogeneous modern materials. The development of accelerated corrosion tests that simulate the long-term behavior of phosphorus-rich iron in atmospheric environments has been an important practical outcome of the Delhi pillar research. The accelerated tests, which use cycles of wetting and drying in controlled atmospheric conditions to simulate the natural climatic cycle of Delhi, can produce in weeks or months the same type of protective film that requires centuries to form naturally. These accelerated tests have been used to evaluate the corrosion resistance of experimental iron alloys with different phosphorus contents and different compositions, providing data that is directly relevant to the development of new corrosion-resistant materials. The question of whether the protective mechanism of the Delhi pillar can be applied to the protection of existing iron and steel structures is one of the most practical questions that the pillar research has raised. The application of a phosphorus-containing treatment to the surface of an existing iron or steel structure, promoting the formation of a misawite-like film in situ, is a concept that has been explored by corrosion protection researchers, and that has shown promising results in laboratory tests. The development of practical phosphorus-based surface treatments for the protection of existing structures would be a significant advance in the field of corrosion protection because it would provide a simple, inexpensive, and environmentally friendly alternative to the paints, coatings, and cathodic protection systems that are currently used to protect iron and steel from atmospheric corrosion. The role of the slag inclusions in the Delhi pillar's iron in the overall corrosion behavior of the pillar has been investigated in detail by Balasubramaniam and his colleagues. The slag inclusions, which are present throughout the iron as a consequence of the bloomery smelting process, create local variations in the chemistry of the iron surface that influence the formation and the structure of the protective film. The analysis of the film in the vicinity of slag inclusions has revealed that the film is thicker and more complex at these locations, reflecting the local differences in the chemistry between the slag and the iron. The slag inclusions in the Delhi pillar's iron are composed primarily of iron silicate, a glassy material that is the residue of the smelting process. The composition of the slag, which includes silica, iron oxide, alumina, and smaller quantities of other compounds, is consistent with the slag that would be produced by the smelting of laterite iron ore, the type of ore that is most commonly found in the iron-producing regions of central and southern India. The identification of the slag as laterite-derived provides additional evidence for the geographical origin of the ore that was used to produce the pillar's iron. The distribution of the slag inclusions within the iron is not uniform, but follows a pattern that reflects the specific techniques of forging and welding that were used to construct the pillar. The slag inclusions are concentrated along the interfaces between the original blooms, the surfaces where the blooms were welded together during the construction of the pillar, and they are less numerous in the centers of the original blooms, where the forging process was most effective in expelling the slag. The pattern of slag distribution provides information about the specific techniques of forging and welding that were used, including the number of forgings that each bloom underwent, the direction of the hammer butts, and the quality of the welds. The investigation of the corrosion behavior of the slag inclusions themselves has revealed that the slag is more resistant to corrosion than the iron, a finding that has implications for the overall corrosion behavior of the pillar. The slag inclusions, which project slightly above the surface of the iron as the iron corrodes preferentially around them, create a microtopography on the surface of the pillar that influences the flow of water and the formation of the protective film. The slight projection of the slag inclusions above the iron surface creates channels that direct the flow of rainwater across the surface, promoting the dissolution and the redistribution of the phosphorus compounds that form the protective film. The question of whether the specific type of slag that is found in the Delhi pillar's iron contributes to the corrosion resistance of the pillar beyond the contribution of the phosphorus is one that has been investigated by corrosion scientists. The slag inclusions, which contain silica and other compounds that are known to promote the formation of passive films on iron surfaces may provide additional protection against corrosion that supplements the protection provided by the phosphorus-mediated misawite film. The investigation of this possibility is ongoing, and the results may provide additional insights into the complex interplay of chemical and microstructural factors that contribute to the pillar's extraordinary corrosion resistance. The broader question of what the Delhi pillar's corrosion behavior tells us about the general principles of atmospheric corrosion protection has been explored by corrosion scientists who have used the pillar as a case study in the development of improved corrosion protection strategies. The pillar demonstrates that the most effective corrosion protection is provided by a dense, adherent, self-healing film that forms spontaneously on the surface of the metal through the interaction of specific chemical components within the metal with the specific chemical conditions of the environment. The pillar also demonstrates that the formation of such a film is a slow process that requires centuries to reach its full protective capability, a timescale that is far longer than the timescales that are typically considered in the design of modern corrosion protection systems. The concept of passive film engineering, the deliberate design of metallic materials and surface treatments that promote the formation of protective passive films in specific environmental conditions, is one of the most promising applications of the principles demonstrated by the Delhi pillar. The development of new metallic alloys that contain specific chemical additives, such as phosphorus, that promote the formation of dense, adherent passive films in atmospheric conditions could produce materials with corrosion resistance that approaches or exceeds that of the Delhi pillar's iron, and the potential benefits of such materials for the infrastructure, the construction, and the manufacturing industries are enormous. The question of whether the specific smelting conditions used by the Indian ironworkers contributed to the uniform distribution of phosphorus in the iron, a distribution that is essential for the formation of a continuous protective film, has been investigated through experimental replications of the Indian bloomery process. The experiments have shown that the temperature and the reducing conditions within the bloomery furnace influence the degree to which the phosphorus from the ore is incorporated into the iron, with higher temperatures and more strongly reducing conditions promoting greater phosphorus incorporation and more uniform distribution. The specific smelting conditions that were used by the Indian ironworkers, which included relatively high temperatures achieved through the use of efficient bellows systems and relatively strong reducing conditions created by the use of charcoal as both the fuel and the reducing agent, were favourable for the incorporation of phosphorus into the iron. The charcoal-fueled bloomery process, which was the standard method of iron production in India for over 2,000 years, created conditions that promoted the transfer of phosphorus from the ore to the iron, producing an iron with the high phosphorus content that is the foundation of the corrosion resistance observed in the Delhi pillar. The comparison between the Indian bloomery process and the bloomery processes used in other parts of the world provides additional context for understanding why the corrosion-resistant iron was produced specifically in India. The bloomery processes used in Europe, which typically employed lower phosphorus ores and different furnace designs, produced iron with lower phosphorus contents that did not develop the same protective film. The European ironworkers, who used ores from geological formations that were different from the Indian ores, did not have access to the phosphorus-rich raw materials that were essential for the production of corrosion-resistant iron, and their iron, despite being produced by a fundamentally similar process, did not develop the specific corrosion-resistant properties that characterize the Indian iron. The specific geological formations that provided the phosphorus-rich ores for the Indian iron industry have been identified through geological survey and through the chemical analysis of ore samples from the traditional iron-producing regions. The laterite ores of central and southern India, which are weathered surface deposits that have been enriched in iron through millions of years of tropical weathering, are particularly rich in phosphorus. because the phosphorus, which is present in the parent rock as a component of the mineral apatite, is concentrated in the laterite, along with the iron during the weathering process. The concentration of phosphorus in the laterite ores is typically in the range of 0.1 to 0.5%, a concentration that is sufficient to produce iron with the high phosphorus content that is needed for corrosion resistance. The question of whether the specific laterite deposits that were used to produce the iron of the Delhi pillar can be identified is one that has been pursued through the comparison of the trace element composition of the pillar's iron with the trace element compositions of laterite ores from different regions. The trace element fingerprint of the iron, which includes the concentrations of phosphorus, silicon, manganese, copper, nickel, and other elements, can potentially be matched to the trace element fingerprint of a specific ore source, providing information about the geographical origin of the raw material. The analysis conducted to date has suggested that the ore came from the laterite deposits of the Vindhyan region of central India, which is consistent with the historical evidence that places the original location of the pillar in the Udayagiri Vidisha region of Madhya Pradesh. The investigation of the specific conditions under which the misawite film achieves its maximum protective capability has been one of the most practically relevant aspects of the Delhi pillar research. The research has shown that the film's protective capability depends on several factors, including the phosphorus content of the iron, the frequency and the duration of the wet-dry cycles, the temperature during both the wet and the dry phases, and the presence of pollutant species in the atmosphere. The optimization of these factors, which can be controlled in a laboratory setting, but which are determined by the natural climate in the case of the Delhi pillar, is essential for maximizing the corrosion protection that the film provides. The mathematical modeling of the film formation process, using equations that describe the rates of dissolution, precipitation, and diffusion of the phosphorus and iron species in the film, has been used to predict the long-term behavior of the film under different environmental conditions. The models, which have been validated by comparison with the measured properties of the film on the Delhi pillar, predict that the film will continue to grow and to improve for several more centuries before reaching its maximum thickness and its maximum protective capability. The prediction that the film has not yet reached its full potential is a striking finding because it suggests that the Delhi pillar's corrosion resistance is still improving after 1600 years, and that the pillar will be even more corrosion resistant in the future than it is today. The experimental validation of the misawite film's self-healing capability has been one of the most important confirmations of Balasubramanian's model. In controlled laboratory experiments, researchers have deliberately scratched or damaged the protective film on samples of phosphorus-rich iron and have then exposed the damaged samples to the cyclic wet-dry conditions that simulate the Delhi climate. The results have consistently shown that the damaged areas of the film are repaired within a few wet-dry cycles, with new misawite forming at the damaged sites and sealing the exposed iron from further corrosion. The speed and the completeness of the repair process are impressive, with the damaged areas showing full recovery of their protective properties within weeks of the damage being inflicted. The self-healing capability of the film has been quantified using electrochemical impedance spectroscopy, which measures the electrical resistance of the film as a function of time after the damage has been inflicted. The measurements that the resistance of the damaged areas increases rapidly as the new misawite forms, reaching values that are comparable to the resistance of the undamaged film within a few weeks. The rapid recovery of the protective properties is a direct consequence of the phosphorus reservoir in the bulk iron, which provides a continuous supply of the phosphorus that is needed for the formation of new misawite at the damaged sites. The long-term sustainability of the self-healing mechanisms depends on the continued availability of phosphorus in the bulk iron, and the question of whether the phosphorus reservoir will eventually be exhausted has been addressed by Balasubramanian through calculations of the total amount of phosphorus in the pillar and the rate at which it is consumed by the film formation process. The calculations show that the total amount of phosphorus in the pillar's iron is sufficient to sustain the self-healing mechanism for many more centuries, possibly for tens of thousands of years, given the extremely slow rate at which the phosphorus is consumed. The self-healing mechanism is therefore not a temporary protection that will eventually fail, but a permanent protection that will continue to operate for as long as the iron of the pillar contains phosphorus. The scientific investigation of the iron pillar of Delhi has been conducted over a period of more than a century and a half, and it has involved researchers from India, from Europe, and from around the world. The investigation has proceeded along several major tracks, each of which has produced important results, and each of which has contributed to the comprehensive understanding of the pillar that exists today. The first major track of investigation has been the chemical analysis of the pillar's iron, aimed at determining the specific composition that gives the iron its unusual properties. The earliest chemical analyses of the pillar's iron were conducted in the mid-19th century, when British colonial officials commissioned the analysis of samples that had been removed from the pillar. These early analyses, which used the wet chemical methods that were standard at the time, revealed that the iron was of unusually high purity, with a low content of carbon, approximately 0.08%, and low contents of sulfur, silicon, and manganese, the impurities that are typically present in ancient iron. The early analyses also detected the presence of phosphorus at a concentration of approximately 0.25%, but the significance of this finding was not recognized until much later. The recognition that the phosphorus content of the iron was the key to the pillar's corrosion resistance was the result of the work of Balasubramaniam and his colleagues, who published their findings in a series of papers in the late 1990s and early 2000s. Balasubramaniam's analysis of the protective film on the pillar's surface, which used techniques including X-ray diffraction, Fourier transform infrared spectroscopy, Mossbauer spectroscopy, and scanning electron microscopy with energy dispersive X-ray spectroscopy, identified the film as iron hydrogen phosphate hydrate, the mineral misawite, and demonstrated that the formation of the film was dependent on the high phosphorus content of the iron. The second major track of investigation has been the study of the protective film itself, aimed at understanding its composition, its structure, and the mechanism by which it protects the iron from corrosion. Balasubramaniam's analysis of the film revealed that it has a complex, layered structure with an inner layer that is in direct contact with the iron surface and an outer layer that is in contact with the atmosphere. The inner layer is composed primarily of iron phosphate compounds, while the outer layer is composed of a mixture of iron phosphate and iron oxide compounds. The layered structure of the film, which is a consequence of the cyclic nature of the film formation process, contributes to the film's effectiveness as a corrosion barrier because the multiple layers provide redundant protection against the penetration of moisture and oxygen. The thickness of the protective film has been measured by cross-sectional examination of samples that have been removed from the pillar's surface. The film is approximately 50 micrometers thick, roughly half the thickness of a sheet of paper, and it is strikingly uniform, with a consistent thickness and a consistent composition across the entire surface of the pillar. The uniformity of the film is evidence of the uniformity of the phosphorus distribution in the iron, because the film can form only where phosphorus is present, and the consistent thickness of the film indicates that the phosphorus is distributed evenly throughout the iron rather than being concentrated in specific regions. The electrochemical properties of the protective film have been studied using techniques that measure the electrical resistance and the electrochemical potential of the film in simulated atmospheric conditions. These measurements have confirmed that the film is an effective barrier to the electrochemical reactions that cause corrosion, presenting a high electrical resistance that prevents the flow of electrical current between the iron surface and the atmosphere. The electrochemical measurements have also confirmed that the film is self-healing, with damaged areas of the film showing rapid recovery of their protective properties as new misawite is formed to seal the damage. The third major track of investigation has been the study of the pillars' construction techniques, aimed at understanding how the ancient Indian ironworkers produced a 6.5-ton iron pillar using the bloomery process. The construction of the pillar required the production, the forging, and the welding of a large number of individual iron blooms, each weighing a few kilograms, into a single, coherent structure that has maintained its structural integrity for 16 centuries. The numbers are striking when we consider the scale of the metalworking enterprise that was required to produce the pillar. The production of 6.5 tons of iron using the bloomery process, assuming an average bloom weight of approximately 5 kilograms and a typical yield of approximately 50%, would have required the smelting of approximately 13 tons of iron ore and the consumption of approximately 26 tons of charcoal. The smelting alone would have required approximately 1,300 individual smelts, each taking several hours to complete, and the forging and welding of the resulting blooms would have required additional weeks or months of continuous work by a team of skilled ironworkers. The welding technique that was used to join the individual blooms into a single pillar is one of the most impressive aspects of the pillar's construction. The welding of iron blooms is accomplished by heating the blooms to a white-hot temperature and then hammering them together, forcing the surfaces of the two blooms into intimate contact and allowing the iron atoms at the surfaces to bond together. The quality of the weld depends on the temperature, the pressure, and the cleanliness of the surfaces, and a good weld produces a joint that is essentially indistinguishable from the surrounding metal. The examination of the Delhi pillar's internal structure, using techniques such as ultrasonic testing and gamma-ray radiography, has revealed that the weld joints are of exceptionally high quality, with minimal porosity and minimal inclusion content, indicating a level of welding skill that is impressive by any standard. The fourth major track of investigation has been the comparison of the Delhi pillar with other ancient iron objects, aimed at determining whether the corrosion resistance of the pillar is unique, or whether it is shared by other iron objects that were produced using similar techniques and similar raw materials. The comparison has revealed that the Delhi pillar is not entirely unique in its corrosion resistance. Several other ancient Indian iron objects, including iron beams, iron clamps, and iron tools that were produced using similar phosphorus-rich ores and similar smelting techniques, exhibit similar corrosion resistance, though none of them has been studied as extensively as the Delhi pillar. The iron beams of the Konark Sun Temple in Odisha, which were produced approximately 800 years after the Delhi pillar, are among the most important comparative examples. The Konark beams, which were used as structural supports in the construction of the temple, are made of an iron that is similar in composition to the Delhi pillar's iron, with a high phosphorus content and a low carbon content. The beams exhibit similar corrosion resistance to the pillar, with a protective film of iron phosphate compounds on their surfaces that has preserved them from significant corrosion over a period of approximately 8 centuries. The similarity between the Delhi pillar and the Konark beams confirms that the corrosion resistance is a systematic property of Indian bloomery iron produced from phosphorus-rich ores, rather than a unique property of the Delhi pillar alone. The investigation of the iron clamps that were used to hold together the stone blocks of ancient Indian temples has provided additional comparative evidence. These iron clamps, which are found at temple sites across India, are made of bloomery iron that is often similar in composition to the Delhi pillar's iron, and many of them exhibit corrosion resistance that is consistent with the phosphorus-mediated protection mechanism that has been identified in the Delhi pillar. The iron clamps provide evidence that the corrosion-resistant properties of Indian bloomery iron were exploited, whether intentionally or accidentally, in a wide range of structural applications, not only in the production of monumental pillars, but also in the everyday construction practices of the ancient Indian builders. The fifth major track of investigation has been the attempt to reproduce the corrosion resistance of the Delhi pillar's iron using modern metallurgical techniques. Several research groups have produced experimental iron alloys with compositions that are similar to the Delhi pillar's iron, including a high phosphorus content and a low carbon content, and they have tested the corrosion resistance of these alloys under simulated atmospheric conditions. The results of these experiments have confirmed that the high phosphorus content is the key factor in the corrosion resistance, with phosphorus-rich iron alloys consistently outperforming phosphorus-poor iron alloys in corrosion tests. The modern experiments have also revealed the specific conditions under which the protective misawite film forms most effectively. The film formation is promoted by the alternation of wet and dry conditions, as occurs in the natural climatic cycle of Delhi, and it is inhibited by continuous immersion in water, or by continuous exposure to a dry atmosphere. The cyclic wet-dry exposure is essential for the formation of the dense, adherent film that provides the maximum corrosion protection, and the specific climatic conditions of Delhi, with its distinct wet monsoon season and dry winter season, are particularly favourable for the film formation process. The sixth major track of investigation has been the study of the pillar's history, its original location, and the circumstances of its erection and its subsequent movement. The inscription on the pillar, which attributes it to King Chandra and describes its erection on a hill called Vishnupadagiri, has been the subject of extensive scholarly analysis by historians and epigraphers who have sought to identify the specific king and the specific location to which the inscription refers. The identification of King Chandra with the Gupta Emperor Chandragupta II is the most widely accepted interpretation, though other identifications have been proposed. The identification is based on the style of the inscription, which is consistent with the epigraphic conventions of the Gupta period, and on the specific titles and epithets that are used in the inscription, which are consistent with the known titles of Chandragupta II. The military achievements that are described in the inscription, including the conquest of enemies in the east and the west, and the crossing of a river that is identified as the Sindhu, are consistent with the known military campaigns of Chandragupta II, who was one of the most powerful and most successful military leaders of the Gupta period. The original location of the pillar, Vishnupadagiri, has been the subject of debate among historians and archaeologists. The most widely accepted identification is with the site of Udagiri in Madhya Pradesh, where a complex of rock-cut caves and a monumental stone inscription from the Gupta period have been found. The identification of Vishnupadagiri with Udayagiri is based on the astronomical alignment of the caves, which are oriented toward the position of the sun on specific dates, and on the presence of a socket hole at the top of the hill that is consistent with the base of a large pillar. If the identification is correct, the pillar was originally erected at Udayagiri, approximately 600 kilometers south of Delhi, and was subsequently moved to its present location, probably by the rulers of the Delhi Sultanate, in the 11th or 12th century. The question of how the pillar was moved from Udayagiri to Delhi is one that has been investigated by engineers and historians who have studied the logistics of transporting a 7-meter, 6.5-ton iron column over a distance of 600 kilometers using pre-modern technology. The transportation in of such a heavy and awkwardly shaped object would have required the construction of a specialized cart or sled, the preparation of the road surface, and the use of teams of animals or of human laborers to pull the vehicle. The transportation would have been a major logistical undertaking that would have required weeks or months to complete, and the fact that it was carried out successfully without damaging the pillar is evidence of the organizational capabilities and the engineering skills of the rulers who ordered the move. The question of why the pillar was moved from Udayagiri to Delhi is also debated. The most commonly cited explanation is that the pillar was moved to Delhi as a trophy of conquest, a symbol of the new ruler's power over the territories that the pillar represented. The erection of the pillar in the courtyard of the Quattul Islam Mosque, which was built on the site of a destroyed Hindu temple, was a deliberate act of political and religious symbolism that placed the pillar, with its Hindu inscription and its Hindu associations, within the context of the new Islamic rule. The modern study of the iron pillar has benefited from the application of non-destructive testing techniques that allow the internal structure and the composition of the pillar to be examined without removing samples from the surface. The application of gamma-ray radiography, which uses the penetrating radiation of gamma rays to produce images of the internal structure of the metal, has revealed the weld joints between the individual blooms, the distribution of slag inclusions within the iron, and the overall structural integrity of the pillar. The application of ultrasonic testing, which uses high-frequency sound waves to detect internal flaws and interfaces, has provided complementary information about the internal structure. These non-destructive techniques have been essential for the study of the pillar because the removal of samples from the surface would damage the protective film and would compromise the pillar's corrosion resistance. The potential applications of the knowledge gained from the study of the Delhi pillar for modern corrosion protection have been explored by researchers in the field of corrosion science. The phosphorus-mediated corrosion resistance mechanism that protects the Delhi pillar could, in principle, be applied to modern iron and steel products by the deliberate addition of phosphorus to the alloy in controlled quantities. Modern weathering steels, which contain small additions of copper, chromium, nickel, and phosphorus that promote the formation of a protective patina, are a modern application of a similar principle, though the specific mechanism of protection in weathering steels is different from the mechanism in the Delhi pillar. The development of phosphorus-containing coatings and surface treatments that replicate the protective properties of the Delhi pillar's misawite film is another area of active research. Several research groups have developed phosphate-based coatings for iron and steel that are inspired by the natural film on the Delhi pillar and that provide enhanced corrosion protection in atmospheric environments. These coatings, which are applied to the surface of the metal as a chemical treatment rather than as a paint or a physical barrier, produce a film that is similar in composition, in structure, to the natural film on the Delhi pillar, and that provides comparable corrosion protection. The seventh major track of investigation has been the study of the pillar's microstructure, which provides information about the specific techniques that were used in its production and about the thermal and mechanical history that the iron has undergone. The microstructure of the pillar's iron, which has been examined using optical microscopy and scanning electron microscopy, is characteristic of bloomery iron that has been extensively forged with a matrix of ferrite grains, the low-carbon phase of iron, interspersed with inclusions of slag and with bands of phosphorus-enriched iron that reflect the specific conditions of the smelting and the forging processes. The ferrite grains in the pillar's iron are relatively large, with an average grain size of approximately 50 to 100 micrometers, indicating that the iron was forged at relatively high temperatures and was allowed to cool slowly, conditions that promote the growth of large grains. The large grain size, while it reduces the strength of the iron slightly, contributes to its corrosion resistance by reducing the total area of grain boundaries, which are sites of preferential corrosion in most metallic materials. The specific grain size of the pillar's iron is therefore another factor, in addition to the phosphorus content, that contributes to the pillar's corrosion resistance. The slag inclusions in the pillar's iron are another important microstructural feature that has been studied by researchers. The slag inclusions, which are small particles of the non-metallic residue of the smelting process that were trapped in the iron during the forging and the welding operations, are typical of bloomery iron and are present in all ancient iron objects that were produced by the bloomery process. The composition of the slag inclusions in the pillar's iron has been analysed by energy dispersive X-ray spectroscopy and has been found to be consistent with the slag that would be produced by the smelting of the specific types of ore that are found in the iron-producing regions of central India. The distribution of phosphorus within the pillar's iron has been mapped using electron probe microanalysis, a technique that measures the concentration of specific elements at specific locations within a sample with a spatial resolution of a few micrometers. The phosphorus mapping has revealed that the phosphorus is distributed relatively uniformly throughout the iron, with some local enrichment near the slag inclusions and at the grain boundaries. The uniform distribution of the phosphorus is consistent with the hypothesis that the phosphorus was incorporated into the iron during the smelting process, when the phosphorus from the ore dissolved into the molten or semi-molten iron and was distributed throughout the metal as it solidified. The phosphorus content of the Delhi pillar's iron, approximately 0.25%, is significantly higher than the phosphorus content of most modern steels, but it is within the range of phosphorus contents that have been measured in other ancient Indian bloomery irons. The analysis of iron objects from archaeological sites across India has revealed that the phosphorus content of Indian bloomery iron varies widely from less than 0.01% to more than 0.5%, depending on the specific ore that was used. The ores from specific regions, particularly the ores from the laterite deposits of central and southern India, are particularly rich in phosphorus, and the iron produced from these ores tends to have the high phosphorus content that is associated with enhanced corrosion resistance. The investigation of the specific techniques of forge welding that were used to construct the Delhi pillar has been an important aspect of the research, because the forge welding of multiple blooms into a single coherent pillar is one of the most technically demanding aspects of the pillar's construction. The forge welding process involves heating the surfaces of two pieces of iron to a temperature at which the iron is soft enough to flow under the pressure of the hammer blows, and then hammering the two pieces together so that the surfaces merge and bond, forming a continuous solid mass. The quality of a forge weld depends on several factors, including the temperature of the weld, which must be high enough to allow the iron to flow, but not so high that the iron begins to melt or to burn. The cleanliness of the surfaces, which must be free of oxide scale and other contaminants that would prevent the surfaces from bonding. And the force and the speed of the hammer blows, which must be sufficient to deform the iron and to force the surfaces into intimate contact. The achievement of a good forge weld requires considerable skill and experience, and the consistently high quality of the welds in the Delhi pillar is evidence of the exceptional skill of the ironworkers who produced it. The specific technique that was used to build up the mass of the pillar from individual blooms has been inferred from the internal structure of the pillar, as revealed by gamma-ray radiography. The radiographic images show that the pillar was constructed by stacking and welding blooms in a specific pattern, building up the mass of the pillar layer by layer, with each layer consisting of several blooms that were welded together laterally and then welded to the layer below. The specific pattern of welding varies along the length of the pillar, reflecting the changing diameter and the changing cross-sectional area of the pillar from base to top. The decorative capital at the top of the pillar, which originally supported a figure of the god Vishnu's Mount Garuda, was produced by a different technique than the body of the pillar. The capital was cast or forged separately and was then welded to the top of the pillar, and the quality of the weld between the capital and the body is consistent with the high quality of the welds throughout the pillar. The original Garuda figure that surmounted the capital has been lost, probably removed during the pillar's relocation to Delhi or during the subsequent construction of the mosque complex. The estimation of the number of workers and the amount of time required to produce the Delhi pillar has been attempted by several researchers using the known productivity of traditional Indian bloomery furnaces and the known rates of forging and welding as a basis for their calculations. The estimates vary widely, but a typical estimate suggests that the production of the pillar would have required a team of approximately 50 to 100 ironworkers, including smelters, forgers, and support workers, working for a period of approximately 3 to 6 months. The scale of the labour force and the duration of the production process indicate that the pillar was a major industrial project that required the coordination of a significant number of skilled workers and the investment of substantial resources. The relationship between the iron pillar of Delhi and the broader tradition of pillar erection in Indian civilization provides important cultural context for understanding the significance of the pillar. The erection of pillars Columns and standards was a widespread practice in ancient India, with examples ranging from the stone pillars of the Mauryan Emperor Ashoka, which date to the 3rd century before the Common Era, to the iron pillars and copper pillars that were erected by the rulers of the Gupta and the post-Gupta periods. The tradition of pillar erection in India was connected to both religious and political functions, with pillars serving as symbols of royal authority, as markers of territorial claims, and as devotional objects dedicated to specific deities. The Ashokan pillars, which are among the earliest and the most famous examples of the Indian pillar tradition, were carved from single blocks of polished sandstone and were inscribed with the edicts of the Emperor Ashoka, which promoted the principles of non-violence, tolerance, and moral conduct. The Ashokan pillars were technological achievements in their own right, requiring the quarrying, the transportation, and the erection of stone columns that were up to 15 meters tall and that weighed up to 50 tons. The tradition of pillar erection that began with Ashoka continued through the subsequent centuries and was adapted by later rulers, including the Gupta emperors, who commissioned both stone and iron pillars as symbols of their power and their devotion. The specific religious significance of the Delhi pillar, which was dedicated to the god Vishnu, and which originally supported a figure of Garuda, Vishnu's mount, places the pillar within the tradition of Vaishnavite devotional architecture that was one of the most important artistic and religious traditions of the Gupta period. The Vaishnavite temples and shrines of the Gupta period, which are among the finest examples of Indian religious architecture, incorporated pillars, columns, and other architectural elements that were designed to express the devotion of the patron to the god Vishnu and to demonstrate the patron's power and piety. The erection of the Delhi pillar as a victory standard, commemorating the military achievements of King Chandra, connects the pillar to the tradition of victory pillars and victory columns that was common in the ancient world. The Roman column of Trajan, which commemorates the Emperor Trajan's campaigns in Dacia, and which is decorated with a spiral relief depicting scenes from the campaigns, is the most famous example of the victory column tradition in the Western world. The Delhi pillar serves a similar function in the Indian tradition, commemorating the victories of King Chandra and demonstrating his power and his devotion to the gods. The comparison between the Delhi pillar and the other large iron objects that survive from ancient India provides evidence for the scope and the sophistication of the ancient Indian iron industry. The iron beams of the Konarak Sun Temple, which we have already mentioned, are approximately 7 meters long and weigh approximately 10 tons each, making them among the largest forged iron objects in the ancient world. The iron cannon, known as the Maliki Maiden, which was cast in the 16th century and which weighs approximately 55 tons, is one of the largest cast iron objects in the pre-modern world. These objects, together with the Delhi pillar, demonstrate that the Indian metallurgical tradition was capable of producing iron and steel objects of exceptional size and quality, and that the specific achievement of the Delhi pillar was part of a broader tradition of metallurgical excellence that produced remarkable results across multiple centuries and multiple technologies. The investigation of the Delhi pillar by international research teams has produced a body of knowledge that extends well beyond the specific questions of the pillar's composition and its corrosion resistance. The research has contributed to the broader understanding of ancient Indian metallurgy, of the techniques and the materials that were used by the Indian ironworkers, and of the social and the economic organization of the Indian iron industry. The Delhi pillar has served as a focal point for interdisciplinary research that has brought together metallurgists, archaeologists, historians, and corrosion scientists in a collaborative investigation that has produced insights that none of these disciplines could have achieved alone. The collaboration between Indian and international researchers has been a distinctive and a productive feature of the Delhi pillar research. The Indian researchers, who possess intimate knowledge of the Indian metallurgical tradition and of the specific environmental and cultural conditions that influenced the production and the preservation of the pillar, have contributed a perspective that is essential for the proper interpretation of the analytical results. The international researchers who bring expertise in analytical techniques, in corrosion science, and in comparative metallurgy have contributed tools and methods that has been essential for the detailed characterization of the pillar's iron and its protective film. The collaboration between these two groups has been a model for international research cooperation and has demonstrated the value of combining local knowledge with global expertise in the investigation of complex archaeological and materials science problems. The publication of the Delhi Pillar research in leading international scientific journals, including the journals of the Institute of Metals, the journals of the Electrochemical Society, and the journals of the American Chemical Society, has ensured that the results are available to the global scientific community and that the insights gained from the study of the pillar can be applied to the development of new materials and new corrosion protection technologies around the world. The wide dissemination of the research results has also contributed to the recognition of the Indian metallurgical tradition as one of the most important and most sophisticated in the ancient world, a recognition that is long overdue and that the Delhi Pillar research has done much to advance. The potential for the discovery of additional ancient Indian iron objects that exhibit the same corrosion resistance as the Delhi Pillar is significant. The iron-producing regions of India contain numerous archaeological sites where iron objects from the ancient and the medieval periods have been found, and the systematic analysis of these objects for their phosphorus content and their corrosion resistance could potentially identify additional examples of the phosphorus-mediated corrosion protection mechanism. The identification of such objects would confirm that the Delhi Pillar is not a unique phenomenon, but a representative of a broader tradition of corrosion-resistant iron production that was practiced across the Indian subcontinent. The application of modern non-destructive testing techniques to the study of the Delhi Pillar and other large ancient iron objects has been an important methodological advance that has allowed researchers to examine the internal structure of these objects without causing any damage. The use of neutron radiography, which uses beams of neutrons to penetrate metallic objects and to produce images of their internal structure, has been proposed as a technique for examining the weld joints and the slag inclusions within the Delhi Pillar without removing any material from the pillar's surface. The application of neutron radiography to the pillar would provide information about the internal structure that is not available from the gamma-ray radiography that has been used to date, and it would complement the surface analyses that have been the primary source of information about the pillar's composition and its protective film. The role of the Delhi Pillar in the popular imagination of both India and the wider world is an aspect of the pillar's significance that extends beyond its metallurgical properties. In India, the pillar is a source of national pride, a tangible proof of the technological achievements of the ancient Indian civilization, and a symbol of the continuity of Indian cultural and technological traditions across millennia. The pillar is featured in Indian educational curricula, in Indian museum exhibitions, and in the popular media as an example of the excellence of ancient Indian metallurgy, and as evidence that India's contributions to world technology extend far beyond the stereotypical associations with mathematics and philosophy. The pillar has also captured the imagination of the international scientific community, which has recognized the pillar as one of the most important examples of ancient materials technology and as a valuable resource for the study of long-term corrosion processes. The international scientific attention has contributed to the recognition of the Indian metallurgical tradition as one of the most important and most sophisticated in the ancient world, and it has helped to correct the historical bias in the history of technology that has tended to undervalue the contributions of non-Western civilizations. The popular legends that have grown up around the pillar, including the belief that embracing the pillar while standing with one's back to it and touching one's hands behind the pillar will bring good luck, reflect the pillar's status as a cultural icon and a source of wonder in the popular imagination. The legends, while they are not scientifically significant, demonstrate the power of the pillar to inspire awe and fascination in people of all backgrounds and all levels of scientific education, and they testify to the universal appeal of an object that defies the ordinary laws of nature and that has survived for longer than anyone expected. The maintenance and the conservation of the Delhi pillar have been the responsibility of the Archaeological Survey of India, which has implemented a range of measures to protect the pillar from damage while maintaining public access to the site. The measures include the construction of a low fence around the pillar to prevent physical contact, the monitoring of the pillar's surface for signs of damage or deterioration, and the periodic assessment of the pillar's structural condition using non-destructive testing techniques. The conservation of the pillar is a long-term commitment that requires the continued attention and the continued investment of the responsible authorities, and the success of the conservation effort to date is a testament to the professionalism and the dedication of the Indian conservation community. The question of whether the Delhi pillar will continue to survive into the future, given the increasing pollution and the changing climate of the Delhi region, is one that has been addressed by researchers who have modelled the long-term behaviour of the protective film under various environmental scenarios. The models suggest that the film will continue to provide effective protection against corrosion for the foreseeable future, even under the more aggressive atmospheric conditions that are expected as a result of increasing pollution and climate change. The film's self-healing mechanism, which continuously repairs any damage to the film caused by environmental attack, provides a resilient defense against the changing conditions, and the pillar's survival for another 16 centuries, while it cannot be guaranteed, appears to be a realistic prospect based on the current scientific understanding of the protection mechanism. The investigation of the Delhi pillar's structural engineering, beyond the metallurgical aspects, has revealed features that demonstrate the ancient Indian builder's understanding of the mechanical principles that govern the stability of a freestanding column. The pillar is tapered, with a larger diameter at the base and a smaller diameter at the top, a design that reduces the weight of the upper portion and lowers the center of gravity, improving the stability of the column against overturning by wind forces or by seismic loading. The taper is not uniform, but follows a slight curve that distributes the weight of the column more efficiently along its length, reducing the stress concentrations that would occur in a column with a uniform cross-section. The foundation of the pillar, which consists of the buried portion of the column, plus a surrounding mass of compacted earth and stone, has been designed to provide a stable base that distributes the weight of the column over a sufficient area to prevent settling or tilting. The pillar has maintained its vertical alignment over 16 centuries, despite being subjected to earthquakes, to the vibrations of nearby construction activity, and to the slow settling of the soil, a testament to the effectiveness of the foundation design and to the structural integrity of the column itself. The surface inscriptions on the pillar have been studied not only for their historical content, but also for the information they provide about the surface condition of the iron at the time the inscription was carved. The depth and the sharpness of the letters indicate that the iron was relatively soft and relatively uniform when the inscription was carved, consistent with the low carbon content and the high purity of the bloomery iron. The preservation of the inscription over 16 centuries, with the letters still sharp and legible, is one of the most compelling visual demonstrations of the pillar's corrosion resistance, because the inscription, which consists of shallow grooves cut into the surface of the iron, would have been the first feature to be obliterated by corrosion if the pillar had corroded at the rate of ordinary iron. The measurement of the pillar's dimensions, which has been conducted with increasing precision over the past century and a half, has provided evidence that the pillar has lost virtually no material to corrosion over its lifetime. The comparison of the current dimensions of the pillar with the estimated original dimensions, based on the construction techniques and the proportions that are typical of Gupta period iron objects, indicates that the pillar has lost less than 1 millimeter of its surface over 1600 years, a rate of material loss that is negligible by any standard, and that is consistent with the extremely low corrosion rate that has been measured by Balasubramanian's electrochemical testing. The question of what the pillar looked like when it was first erected is one that has been addressed by researchers who have attempted to reconstruct the original appearance of the pillar based on the surviving physical evidence and on the descriptions in the inscription. The pillar would originally have been topped by a figure of Garuda, Vishnu's mount, which was mounted on the decorative capital at the top of the column. The surface of the pillar would have been smooth and shiny, with the metallic luster of freshly forged iron, and the inscription would have been prominently visible on the polished surface. The dark, matte finish that the pillar displays today is the result of the gradual formation of the protective film over the centuries, a film that has dulled the surface but that has preserved the underlying iron in essentially its original condition. The Gupta period metalworkers who produced the pillar were working within a tradition that valued both the practical utility and the aesthetic quality of metalwork, and the pillar was designed to be not only structurally sound, but also visually impressive. The graceful taper of the column, the polished surface, the elegant inscription, and the crowning Garuda figure would have combined to produce an object of considerable beauty that expressed the power and the devotion of King Chandra, and that served as a visible symbol of the Gupta dynasty's authority and its patronage of the arts and the sciences. The study of the magnetic properties of the Delhi pillar's iron has provided additional information about its composition and its microstructure. The iron of the pillar is ferromagnetic, as expected for a material that is composed primarily of ferrite, and the magnetic properties of the iron have been measured using techniques that include vibrating sample magnetometry and magnetic force microscopy. The magnetic measurements have confirmed that the iron has a composition and a microstructure that are consistent with a high-purity bloomery iron with a low carbon content and a high phosphorus content, and they have provided additional evidence for the uniformity of the iron's composition across the entire volume of the pillar. The question of whether the pillar's magnetic properties were known to the ancient Indians and whether they were exploited for any purpose is one that has been raised by researchers who have noted that the pillar's iron would have been attracted to other iron objects and to lodestones, the naturally magnetized minerals that were known in the ancient world. The possibility that the pillar's magnetic properties were used for some purpose, such as the alignment of the pillar with the cardinal directions or the demonstration of the attractive properties of iron, is speculative but not implausible, given the ancient Indians' known interest in the properties of materials and their documented knowledge of the attractive properties of lodestones. The application of magnetic techniques to the non-destructive testing of the pillar has been explored as a method of examining the internal structure of the pillar without removing samples. The magnetic methods, which include magnetic flux leakage testing and eddy current testing, can detect internal defects such as cracks, voids, and inclusions without contact with the surface, making them ideal for the examination of heritage objects that must not be damaged. The application of these magnetic techniques to the Delhi pillar could potentially provide additional information about the internal structure and the weld quality that is not available from the gamma-ray radiography that has been used to date. The investigation of the pillar's response to the seismic activity that is known to have occurred in the Delhi region over the past 16 centuries has been conducted by structural engineers who have modelled the dynamic behaviour of the pillar under simulated earthquake loading. The models, which take into account the specific dimensions, the specific material properties, and the specific foundation conditions of the pillar, predict that the pillar is capable of withstanding moderate earthquakes without significant damage, a prediction that is consistent with the pillar's observed survival of the seismic events that are known to have occurred in the Delhi region over the past 16 centuries. Everything we have discussed so far concerns the specific chemistry of the iron pillar of Delhi, the specific composition of its iron, the specific mechanism of its corrosion resistance, and the specific scientific investigations that have revealed these properties. These are important matters, and the research on the Delhi pillar continues to produce results that are relevant to both the understanding of ancient metallurgy and the development of modern corrosion protection techniques. But beneath these specifics lies a deeper truth, a truth that concerns not just what the pillar is, but what it represents, what it tells us about the nature of technological achievement, and what its existence implies about the relationship between intention and accident in the history of materials technology. The deeper truth is this: the iron pillar of Delhi is an accidental masterpiece. The corrosion resistance that has preserved the pillar for 1600 years was not a deliberate achievement of the ancient Indian ironworkers. It was an unintended consequence of the specific raw materials that they used, a consequence that they could not have understood, could not have predicted, and could not have reproduced if they had wanted to, because they did not know the cause of the property they had produced. The ironworkers who forged the pillar were skilled craftsmen who produced an iron object of impressive size and quality, but the property that has made their work famous, the property that has fascinated scientists for over a century, and that has made the Delhi pillar one of the most studied metal objects in the world, was not their achievement. It was the achievement of geology, of the specific mineralogical composition of the ore that they happened to use, an ore that contained the phosphorus that would ultimately protect their work from the ravages of time. This is not science fiction. This is a documented fact that has been confirmed by decades of scientific research. The corrosion resistance of the Delhi pillar is the result of the phosphorus content of the iron, and the phosphorus content is the result of the composition of the ore. The iron workers did not add phosphorus to their iron. They did not know about phosphorus. They did not know about the electrochemistry of corrosion or the chemistry of passive film formation. They produced corrosion-resistant iron by accident, and the accident has preserved their work for 1600 years. The concept of accidental excellence, the achievement of extraordinary results through processes that were not designed to produce those results, is one of the most important themes that the iron pillar of Delhi illustrates. The pillar is not the only example of accidental excellence in the history of materials technology. The carbon nanotubes in Damascus steel, which were produced by forging techniques that were not aimed at producing nanostructured materials, the dichroic nanoparticles in the Lycurgus cup, which were produced by a glass-making process that was not intended to create nanoscale structures, the self-healing lime clasts in Roman concrete, which were produced by a mixing technique that was not designed to create a self-healing mechanism. In each of these cases, an ancient craft tradition produced a material with extraordinary properties that were not intended by the craftsmen who produced them, and that were not understood until the modern era applied its analytical tools to the ancient material. The pattern of accidental excellence that runs through the history of ancient materials technology has profound implications for our understanding of the relationship between intention and achievement in technology. The modern approach to materials development, which is based on the deliberate design of materials with specific properties using the tools of theoretical prediction and computational modeling, assumes that the achievement of specific material properties requires the deliberate intention to achieve them. The examples of accidental excellence that we have encountered in this series demonstrate that this assumption is not always correct, and that specific, valuable, and extraordinary material properties can be achieved through processes that were not designed to produce them. Something is wrong with our assumption that technological achievement requires technological understanding. The ancient Indian ironworkers who produced the Delhi pillar achieved one of the most impressive results in the history of corrosion protection, the preservation of an iron object for 16 centuries in an aggressive atmospheric environment without any understanding of the mechanism that produced this result. Their achievement was not the result of understanding. It was the result of specific conditions, the specific ore, the specific smelting process, the specific climate that happened to converge in a way that produced an extraordinary outcome. The convergence was not planned, it was not predicted. and it could not have been reproduced by the ironworkers if the conditions had changed, because they did not know which conditions were responsible for the result. The vulnerability of accidental excellence to loss is a direct consequence of the absence of understanding. Let that sink in. If the specific ore deposit that provided the phosphorus-rich iron for the Delhi pillar had been exhausted, or if the iron workers had switched to a different ore source, the corrosion-resistant property would have been lost, and the iron workers would not have known why. They could not have corrected the problem because they did not know what was causing the benefit. They could not have reproduced the result with a different ore because they did not know that the ore was the critical factor. The accidental excellence was dependent on specific conditions that the practitioners did not understand and could not control, and the loss of those conditions would have resulted in the loss of the excellence, without the practitioners even knowing that anything had changed. The parallel with other examples of lost technology is instructive. The Damascus steel tradition was lost, at least in part, because the specific ore sources that provided the trace elements necessary for the formation of the characteristic watered pattern were exhausted. The Greek fire formula was lost because the extreme secrecy with which it was guarded prevented the creation of any written record that might have survived the fall of the Byzantine Empire. The technique of Roman concrete was lost because the institutional infrastructure that sustained the knowledge was destroyed during the decline of the Western Roman Empire. In each case, the loss was the result of the failure of specific conditions that the practitioners did not fully understand, and the loss could not be reversed because the practitioners did not know what had been lost or how to recover it. Let that sink in. The iron pillar of Delhi has survived for 1600 years because of a property that its makers did not know it possessed, produced by a mechanism that its makers did not understand, dependent on a raw material whose specific chemical composition its makers could not have known. The pillar is a monument to the power of accident, to the ability of natural processes to produce results that human intention cannot, and to the humbling recognition that the most enduring achievements of human craftsmanship are sometimes the ones that the craftsmen themselves did not plan. The broader implications of the Delhi pillar's story for the modern world are significant. The modern materials science community, which has developed sophisticated tools for the deliberate design of materials with specific properties, can learn from the example of the Delhi pillar that the natural world contains solutions to materials problems that have not yet been deliberately designed, and that may be discovered through the study of ancient materials that achieved those solutions accidentally. The study of ancient materials, including the Delhi pillar, the Damascus steel, the Roman concrete, and the Lycurgus cup, is therefore not merely a historical exercise. It is a practical research program that has the potential to reveal solutions to modern materials problems that have been achieved by accident in the ancient world, and that can be deliberately reproduced and applied in the modern world. The environmental implications of the Delhi pillar's corrosion resistance are also worth considering. The corrosion of iron and steel is one of the most costly and most environmentally damaging problems in the modern world, consuming enormous quantities of energy and materials for the production of replacement structures and for the application of anti-corrosion treatments. The development of iron and steel products that are inherently corrosion resistant, that protect themselves from corrosion through the formation of natural protective films rather than through the application of paints, coatings, and other external treatments, would represent a significant advance in the sustainability and the environmental impact of the construction and the manufacturing industries. The Delhi pillar provides a natural model for such products, a model that has been validated by 16 centuries of real-world performance in one of the most challenging atmospheric environments on Earth. The cultural significance of the Iron Pillar of Delhi extends far beyond its metallurgical properties. The pillar is a symbol of Indian technological achievement, a tangible proof that the ancient Indian civilization possessed capabilities that were, in specific and measurable ways, superior to those of other ancient civilizations, and that remain impressive even by modern standards. The pillar has been celebrated in Indian culture as evidence of the technological sophistication of the ancient Indian world, and it has been cited by scholars and by the general public as a counterexample to the Western-centric narrative of technological progress that presents the development of modern technology as a primarily Western achievement. The recognition that the ancient Indian ironworkers produced iron that is more corrosion-resistant than modern iron, using techniques that were developed through millennia of empirical practice, and that were adapted to the specific raw materials and the specific conditions of the Indian subcontinent, is a recognition that technological excellence is not the exclusive province of any single civilization or any single era. The Delhi Pillar is proof that the practical empirical approach to materials technology, the approach of the ancient craftspeople who worked with their hands and their eyes and their accumulated experience, can produce results that rival and sometimes exceed the results of the theoretical scientific approach that characterizes modern materials science. The question of whether the ancient Indian ironworkers were aware that their iron was more corrosion resistant than the iron produced by other methods or by other civilizations is one that cannot be answered from the surviving evidence. The ancient Indian texts that discuss metalworking, including the treatises on metallurgy that are found in the Sanskrit scientific literature, do not contain any references to corrosion resistance as a property of iron or to any techniques for producing corrosion-resistant iron. The absence of such references does not prove that the ironworkers were unaware of the property, because the written texts may not record all of the practical knowledge that the ironworkers possessed, but it does suggest that corrosion resistance was not a property that the ironworkers deliberately sought, or that they recognized as a distinctive feature of their products. The possibility that the ironworkers recognized the superior durability of their iron through practical experience, without understanding the chemical mechanism that produced it, is consistent with the broader pattern of empirical knowledge in the ancient world. The ironworkers would have observed that iron produced from certain ores lasted longer than iron produced from other ores, and they might have selected the longer-lasting ores for specific applications, such as the production of pillars and other outdoor structures, without knowing why those ores produced more durable iron. The selection of ores based on practical observation of the resulting iron's durability would have been a form of empirical optimization, a process of trial and error that gradually converged on the best available raw materials without any theoretical understanding of the chemistry involved. The broader tradition of Indian metallurgy, which encompassed not only iron and steel production, but also the production of copper, bronze, gold, silver, zinc, and a wide range of alloys, was one of the most diverse and most sophisticated metallurgical traditions in the ancient world. The Indian metallurgists were the first to produce zinc metal by distillation, a technique that was not matched in Europe until the 18th century. They developed brass alloys and bronze alloys of exceptional quality and diversity. They produced the Wootz crucible steel that was the raw material for Damascus steel, and they produced the corrosion-resistant iron that has preserved the Delhi Pillar for 16 centuries. The breadth and the depth of the Indian metallurgical tradition demonstrate that the Delhi Pillar is not an isolated achievement, but a product of a comprehensive metallurgical culture that was among the most advanced in the ancient world. The role of Indian metallurgy in the broader history of world technology deserves greater recognition than it has traditionally received. The Indian contributions to metallurgy, including the development of Wootz steel, the production of corrosion-resistant iron, the invention of zinc distillation, and the development of a wide range of alloys and metalworking techniques, are achievements that rank among the most important in the history of materials technology. The Iron Pillar of Delhi is the most visible and the most famous of these achievements, but it is representative of a broader tradition of metallurgical excellence that extended across the Indian subcontinent and that produced innovations in multiple areas of metals technology over a period of several millennia. The question of whether the specific conditions that produced the Delhi Pillar's corrosion resistance could be deliberately replicated in modern iron production is one that has been explored by researchers in the field of materials science. The deliberate addition of phosphorus to iron in the concentration range that is found in the Delhi Pillars iron is technically straightforward and could be accomplished using modern steelmaking techniques. The production of iron with a phosphorus content of approximately 0.25% is within the capabilities of modern blast furnace and electric arc furnace technology, and the cost of the phosphorus addition would be modest relative to the total cost of the iron production. However, the deliberate addition of phosphorus to modern steel is complicated by the negative effects that phosphorus has on the mechanical properties of the steel. Phosphorus makes steel brittle, reducing its ductility and its impact resistance, properties that are essential for many modern structural applications. The concentration of phosphorus that is needed for effective corrosion protection, approximately 0.25%, is above the threshold at which phosphorus embrittlement becomes a significant concern for most structural applications. The use of phosphorus-rich iron for structural purposes would therefore require a careful balance between the corrosion protection benefits and the mechanical property costs, a balance that would need to be evaluated for each specific application. The development of modern weathering steels, which contain small additions of copper, chromium, nickel, and phosphorus that promote the formation of a protective patina, represents one approach to the incorporation of the Delhi Pillars principles into modern steel production. The weathering steels, which were developed in the mid-20th century and which are widely used for bridges, buildings, and other outdoor structures, form a protective layer of rust on their surfaces that is denser and more adherent than the loose rust that forms on ordinary carbon steel. The protective layer, while it is different in composition from the misawite film on the Delhi pillar, serves a similar function, sealing the surface of the steel and reducing the rate of further corrosion. The comparison between the weathering steels and the Delhi Pillars iron reveals both similarities and differences in the corrosion protection mechanisms. Both materials rely on the formation of a protective surface layer that slows the rate of corrosion. Both layers form spontaneously through the interaction of the metal with the atmosphere, and both layers are self-healing, with damage to the layer being repaired by the continued formation of new protective material. The primary difference is in the composition of the protective layer. The weathering steel layer is composed primarily of iron oxides, while the Delhi Pillars layer is composed primarily of iron phosphates. The iron phosphate layer is denser, more impermeable, and more stable than the iron oxide layer, which explains why the Delhi pillar has survived for 1600 years, while weathering steel structures are designed for a lifespan of approximately 75 to 100 years. The potential for the development of a new generation of corrosion-resistant steels that combine the phosphorus-based protection mechanism of the Delhi pillar with the alloying elements that are used in modern weathering steels is one of the most promising applications of the Delhi pillar research. A steel that contained both the phosphorus needed for the formation of a misawite-like film and the copper, chromium, and nickel that are used in modern weathering steels could potentially form a protective layer that combined the best features of both protection mechanisms, producing a material with a corrosion resistance that approaches or exceeds that of the Delhi pillar. The development of such a material is an active area of research, and the potential economic and environmental benefits of a more corrosion-resistant structural steel are enormous. The relationship between the iron pillar of Delhi and the other examples of ancient materials excellence that we have explored in this series provides a comprehensive picture of the materials capabilities of the ancient world. The Antikythera mechanism demonstrated that the ancient Greeks could build precision-geared mechanical computers. Damascus steel demonstrated that the ancient Indian and Middle Eastern metalworkers could produce nanostructured materials with extraordinary mechanical properties. Greek fire demonstrated that the Byzantines possessed chemical knowledge that has not been fully replicated by modern chemistry. Roman concrete demonstrated that the ancient Romans could produce a building material that is more durable than its modern equivalent. The Lycurgus cup demonstrated that the Romans practiced nanotechnology without knowing it. The Baghdad battery demonstrated that the ancient Mesopotamians may have discovered electrochemistry nearly 2 millennia before Volta. And the iron pillar of Delhi demonstrates that the ancient Indian ironworkers produced a corrosion-resistant iron that has outperformed modern steel for 16 centuries. The cumulative weight of these examples is substantial. Individually, each example might be dismissed as an anomaly, a lucky accident, a one-off achievement that does not represent the general technological capability of the ancient world. But collectively, the examples form a pattern that is too consistent and too impressive to be dismissed. The pattern suggests that the ancient world possessed materials capabilities that were, in specific and measurable respects, equal to or superior to those of the modern world, and that the trajectory of materials technology over the past 2 millennia has not been a simple, continuous progression from primitive to sophisticated, but a complex, uneven process in which specific capabilities have been developed, lost, and in some cases rediscovered over the course of centuries and millennia. The recognition of this pattern has important implications for the way we think about the history of technology and about the relationship between the ancient and the modern worlds. The standard narrative of technological progress, which presents the history of technology as a continuous advancement from primitive to advanced, is contradicted by the evidence of the ancient materials that we have discussed. The narrative needs to be revised to account for the specific capabilities that the ancient world possessed and that the modern world has not yet matched, and to acknowledge that the relationship between the past and the present is more complex and more nuanced than a simple story of progress can capture. The Iron Pillar of Delhi is perhaps the most accessible and the most compelling example in this collection, because the property that makes it extraordinary, corrosion resistance, is a property that is directly relevant to the modern world, and that addresses a problem, the corrosion of iron and steel, that costs the global economy trillions of dollars each year. The pillar is not merely a historical curiosity. It is a practical demonstration of a solution to a modern problem, a solution that was achieved accidentally by ancient ironworkers, and that can, in principle, be adapted and applied by modern materials scientists. The question of whether the principles demonstrated by the Delhi pillar could be applied to the protection of cultural heritage objects, including ancient iron artifacts that are at risk of corrosion, is one that has been explored by conservators and by materials scientists who work in the field of cultural heritage science. The conservation of ancient iron objects is one of the most challenging tasks in the field of heritage conservation, because iron is one of the most reactive and the most corrosion-prone metals, and the environments in which many ancient iron objects are stored or displayed are often not optimized for the long-term preservation of iron. The application of phosphorus-based treatments to the surfaces of corroding ancient iron objects, mimicking the natural process that has protected the Delhi pillar, has been proposed as a conservation technique that could slow or halt the corrosion of these objects. The technique, which would involve the application of a phosphorus-containing solution to the surface of the object, promoting the formation of a misawite-like film that would seal the surface and prevent further corrosion, has been tested on experimental samples and has shown promising results. The development of this technique for routine conservation use would represent a significant advance in the field of iron conservation, providing a treatment that is based on a natural protection mechanism that has been validated by 16 centuries of real-world performance. The comparison between the Delhi pillar and other famous corrosion-resistant artifacts from around the world provides additional perspective on the pillar's significance. The stainless steel that is used in modern architecture and in modern industrial equipment is the most familiar example of a corrosion-resistant metal, but stainless steel achieves its corrosion resistance through the addition of chromium, which forms a thin, transparent oxide film on the surface of the steel. The comparison between the chromium-based protection of stainless steel and the phosphorus-based protection of the Delhi pillar reveals that the two mechanisms are fundamentally different in their chemistry but functionally similar in their effect. Both produce a thin, adherent, self-healing film that seals the surface of the metal and prevents further corrosion. The development of a bio-inspired approach to corrosion protection, in which the natural self-healing mechanisms that are found in biological systems, such as the self-healing of skin wounds, are adapted for use in materials science, has been influenced by the example of the Delhi pillar, which demonstrates that a simple, self-healing protection mechanism can provide effective corrosion protection over extraordinary timescales. The bio-inspired approach, which is a growing area of research in materials science, seeks to develop materials that can repair themselves when damaged, and the Delhi pillar provides one of the most compelling models for this approach, because the pillar's self-healing mechanism has been demonstrated to work over a period that is far longer than any laboratory test can simulate. The broader impact of the Delhi pillar on the development of modern corrosion science has been significant and continues to grow as the implications of the pillar's protection mechanism are explored by researchers around the world. The pillar has demonstrated that the specific chemical composition of a metal, particularly the presence of specific minor alloying elements such as phosphorus, can have a dramatic effect on the metal's long-term corrosion behavior, an insight that has led to the re-evaluation of the role of minor alloying elements in the atmospheric corrosion of iron and steel, and to the development of new alloys and surface treatments that are based on the principles demonstrated by the pillar. The concept of geological serendipity, the accidental convergence of a specific geological conditions with specific technological practices to produce an unexpected and extraordinary result, is one that the iron pillar of Delhi illustrates with particular clarity. The geological serendipity that produced the Delhi pillar's corrosion resistance involved the convergence of three factors: the specific geological formations that produced phosphorus-rich laterite ores in central India, the specific smelting techniques that transferred the phosphorus from the ore to the iron, and the specific climatic conditions of the Delhi region that promoted the formation of the protective misawite film. None of these factors was under the control of the ancient ironworkers. All of them were the products of natural processes, geological, chemical, and climatic, that operated independently of human intention and that converged, by accident, to produce a result that has endured for 16 centuries. The concept of geological serendipity is not unique to the Delhi pillar. The Damascus steel tradition, which depended on specific trace elements in specific Indian ores, is another example of geological serendipity in the history of materials technology. The Roman concrete tradition, which depended on the specific volcanic deposits of Campania for its pozzolanic material, is yet another example. In each case, the specific geological conditions of a particular region provided the raw materials that were needed for the production of a material with extraordinary properties, and the loss of access to these specific raw materials contributed to the eventual loss of the technology. The recognition of the role of geological serendipity in the history of materials technology has important implications for the modern approach to materials development. The modern materials science community, which develops new materials primarily through the deliberate design of compositions and the deliberate optimization of processing conditions, can benefit from the recognition that the natural world contains specific combinations of elements and specific geological formations that have properties that have not been deliberately designed, and that may offer solutions to modern materials problems that have not been considered by the conventional design approach. The systematic exploration of natural materials, including ancient ores, natural mineral deposits, and the products of traditional metallurgical processes for compositions and properties that are relevant to modern applications, is an approach that has been inspired by the study of the Delhi pillar and other ancient materials that have demonstrated unexpected and extraordinary properties. This approach, which has been called geo-inspired materials design, represents a new paradigm in materials science that combines the analytical tools and the theoretical frameworks of modern science with the empirical insights and the natural materials of the geological and the historical record. The question of what the iron pillar of Delhi can teach the modern world about the relationship between materials science and sustainability is one that has gained increasing urgency in the context of the global environmental crisis. The modern construction and manufacturing industries consume enormous quantities of iron and steel, much of which must be protected from corrosion using energy-intensive and environmentally damaging processes. The development of inherently corrosion-resistant materials, inspired by the principles demonstrated by the Delhi Pillar, could significantly reduce the environmental impact of the iron and steel industries and could contribute to a more sustainable approach to materials production and use. The concept of materials longevity, the design and the production of materials that are intended to last for centuries rather than for decades, is one that the Delhi Pillar embodies and that the modern world is only beginning to appreciate. The modern approach to materials production, which is driven by the economics of the market and which values speed, cost, and performance over longevity, produces materials that are optimized for the short term, but that impose enormous long-term costs on society in the form of maintenance, repair, and replacement. The Delhi Pillar's approach, which produces a material that is optimized for longevity and that requires virtually no maintenance or replacement, offers a radically different paradigm that could, if adopted by the modern materials industry, produce benefits that far outweigh the additional initial cost. What does the Iron Pillar of Delhi mean for our understanding of the relationship between ancient craftsmanship and modern science, between empirical knowledge and theoretical understanding, and between the specific and the universal in materials technology? The first implication is a recognition that the most enduring materials solutions are sometimes the simplest ones. The mechanism that protects the Delhi Pillar from corrosion is not a complex, multi-component system that requires specialized maintenance and regular replacement. It is a simple, single-layer film that forms spontaneously on the surface of the iron and that maintains itself through a self-healing mechanism that requires no human intervention. The simplicity of the solution, which is based on the natural chemistry of phosphorus-rich iron in a cyclic wet-dry atmosphere, is one of its greatest strengths because it ensures that the protection is reliable, consistent, and indefinitely sustainable. The contrast between the simplicity of the Delhi Pillar's corrosion protection and the complexity of the anti-corrosion systems that are used in the modern world is striking. Modern corrosion protection relies on a combination of coatings, paints, cathodic protection systems, and corrosion-resistant alloys that are expensive to apply, expensive to maintain, and limited in their effectiveness and their lifespan. The Delhi Pillar's protection, by contrast, requires no application, no maintenance, and no replacement, and it has been effective for 1600 years. The comparison suggests that the modern approach to corrosion protection, which focuses on external barriers and active protection systems, may be less effective in the long term than the ancient approach, which focuses on the intrinsic properties of the material itself. There is a pause worth taking here. Consider the Iron Pillar of Delhi, standing in the open air, exposed to the monsoon rains and the Delhi heat. Its surface protected by a film that is 1/20th of a millimeter thick, a film that has been building itself, layer by layer, for 1600 years. Consider the modern steel bridges and the modern reinforced concrete structures that surround it. Structures that are protected by coatings and systems that must be inspected, maintained, and replaced at regular intervals. Structures that are designed to last for decades rather than for centuries. Consider the cost, in money, in energy, in materials, and in environmental impact, of the constant maintenance and the periodic replacement that the modern approach requires. And consider the possibility that a simpler, more elegant solution, a solution that was achieved accidentally by ancient ironworkers 1600 years ago, might offer a better alternative. The second implication is a recognition of the importance of studying ancient materials as sources of inspiration and of practical knowledge for modern materials science. The Iron Pillar of Delhi is not merely a historical curiosity. It is a practical demonstration of a corrosion protection mechanism that has been validated by 1600 years of real-world performance, a mechanism that has been understood through modern scientific analysis, and that can, in principle, be adapted and applied to modern materials. The study of the pillar has already inspired the development of phosphorus-containing corrosion-resistant alloys and phosphate-based surface treatments that are based on the same chemistry that protects the pillar, and the continued study of the pillar and of other ancient materials has the potential to produce additional insights that are relevant to modern materials technology. The third implication is a reflection on the role of accident in technological achievement. The Iron Pillar of Delhi is an accidental masterpiece, a product of conditions that the ancient ironworkers did not understand and did not control. The recognition of the role of accident in the pillar's achievement does not diminish the accomplishment of the ironworkers, who produced an iron object of impressive size and quality, using techniques that were the product of millennia of accumulated experience. But it does challenge the modern assumption that technological achievement always requires technological understanding, and it reminds us that the most important factor in the development of new materials is sometimes not the deliberate application of scientific theory, but the fortuitous convergence of conditions that produces an unexpected and extraordinary result. The fourth implication is a recognition of the value of long-term thinking in materials technology. The Iron Pillar of Delhi was not designed to last for 1600 years. It was designed, presumably, to last for the lifetime of its patron, and perhaps for a few generations beyond. The fact that it has lasted for 1600 years, and that it shows every sign of lasting for many more centuries to come, is a bonus that was not anticipated by its makers. And that is the result of the accidental corrosion protection that we have described. But the pillar's longevity is a reminder that the materials choices that we make today will have consequences that extend far beyond the lifespan of the people who make them, and that the investment in durable, long-lasting materials, while it may be more expensive in the short term, can produce benefits that far outweigh the initial cost over the long term. The global problem of corrosion, which costs the world economy an estimated $2.5 trillion annually, is a problem that the Delhi Pillar's example suggests could be significantly reduced by the adoption of materials and of surface treatments that are designed for long-term durability rather than for short-term convenience. The development of self-healing corrosion protection systems, inspired by the natural self-healing mechanism of the Delhi Pillar's misawite film, is one of the most promising avenues of research in the field of corrosion science, and the potential economic and environmental benefits of such systems are enormous. The fifth implication of the Iron Pillar story concerns the relationship between preservation and understanding, between the survival of an artifact and the comprehension of its significance. The Delhi Pillar survived for 16 centuries before its corrosion resistance was explained by modern science. During those 16 centuries, the pillar was admired, venerated, and speculated about by the people who saw it, but the specific mechanism that preserved it was unknown. The explanation, when it came, was the product of modern analytical techniques that could examine the pillar's iron and its protective film at the atomic and the molecular level, techniques that did not exist when the pillar was made and that were not applied to the pillar until the late 20th century. The long delay between the pillar's creation and the explanation of its preservation is a reminder that the significance of an artifact may not be apparent at the time of its creation and may not be recognized for centuries or even millennia after it was made. The ironworkers who produced the Delhi Pillar did not know that they were producing a corrosion-resistant iron. The people who admired the pillar for centuries after its erection did not know why it had survived. And the scientists who finally explained the pillar's preservation in the late 20th century were able to do so only because of the development of analytical techniques that were not available to any previous generation of investigators. The lesson for the modern world is that the artifacts of the past may contain knowledge that has not yet been recognized, knowledge that will be revealed only when the appropriate analytical tools and the appropriate theoretical frameworks are developed. The Iron Pillar of Delhi is one such artifact, an object whose significance was revealed by the application of modern materials, science, to ancient iron. Other artifacts may contain similar hidden knowledge that will be revealed by future analytical techniques that have not yet been invented. The investment in the study of ancient artifacts, using the best available tools and the best available theories, is therefore not merely an investment in historical understanding. It is an investment in the future discovery of knowledge that may be relevant to modern technology and that may provide solutions to modern problems. The iron pillar of Delhi has inspired the development of modern phosphorus-enhanced weathering steels and phosphate-based anti-corrosion treatments that are based on the same chemistry that protects the pillar. These modern applications of the ancient principle demonstrate that the study of ancient materials can produce practical benefits for the modern world, and they illustrate the potential for the discovery of additional applications as the study of ancient materials continues, and as the understanding of the principles embodied in those materials deepens. The tourism and the heritage preservation dimensions of the Iron Pillar story deserve mention. The Delhi Pillar is one of the most visited tourist attractions in India, drawing hundreds of thousands of visitors each year who come to see the pillar and to learn about its remarkable properties. The pillar is located within the Qutb Minar complex, a UNESCO World Heritage Site that includes the Qutb Minar, the tallest brick minaret in the world, and a variety of other architectural monuments from the medieval period. The inclusion of the pillar within this important heritage complex ensures its preservation and its accessibility to the public. And the Archaeological Survey of India, which is responsible for the management of the site, has implemented measures to protect the pillar from damage by visitors and by environmental factors. The tradition among visitors of embracing the pillar, wrapping their arms around it, and making a wish was a popular practice that was allowed for many years, but that has recently been restricted by the Archaeological Survey to protect the pillar from the corrosive effects of human sweat, which contains salts and organic acids that could potentially damage the protective film. The restriction of physical contact with the pillar is an example of the balance that must be maintained between public access to heritage objects and the preservation of those objects for future generations, a balance that is particularly important for objects like the Delhi Pillar that are both scientifically valuable and culturally significant. The education of the public about the scientific significance of the Delhi Pillar has been an important aspect of the heritage management of the site. The information panels and the guided tours that are available at the Qutb Minar complex provide visitors with information about the pillar's history, its metallurgy, and the specific mechanism that protects it from corrosion, allowing visitors to appreciate the pillar not only as a historical monument but also as a scientific marvel that has contributed to the modern understanding of corrosion science and materials technology. The question of why the corrosion resistance of the Delhi Pillar was not recognized and exploited earlier in the history of materials science is one that deserves reflection. The pillar has been standing in Delhi for approximately 1,000 years, and its unusual resistance to corrosion has been noted by observers for at least several centuries. The British colonial officials, who first brought the pillar to the attention of the European scientific community in the 19th century, recognized its unusual properties, and the early analyses of the pillar's iron, conducted in the mid-19th century, identified the high phosphorus content that is the key to the corrosion resistance. But the connection between the phosphorus content and the corrosion resistance was not made until the late 20th century, nearly a century and a half after the phosphorus was first detected. The delay in recognizing the significance of the phosphorus content is a cautionary tale about the limitations of scientific analysis when it is not guided by the appropriate theoretical framework. The early analysts who detected the phosphorus in the pillar's iron did not recognize its significance because the role of phosphorus in the formation of corrosion-resistant films was not understood at the time. The phosphorus was noted as an impurity, an anomalous feature of the iron that did not fit the purity hypothesis that was then the prevailing explanation for the pillar's corrosion resistance. The significance of the phosphorus was not recognized until Balasubramanian's work in the late 20th century, when the application of modern analytical techniques and modern theoretical frameworks to the study of the pillar's protective film revealed the phosphorus-mediated corrosion protection mechanism. The lesson is that the significance of a piece of evidence depends on the framework within which it is interpreted, and that the development of new frameworks can reveal the significance of evidence that was previously overlooked or misinterpreted. The phosphorus in the Delhi pillar's iron was detected in the 19th century, but its significance was not recognized until the 20th century, when the development of new analytical techniques and new theoretical models provided the framework within which the phosphorus's role could be understood. The delay in recognition is a reminder that the interpretation of scientific evidence is not a fixed or a final process, but an ongoing process that is continually refined as new tools and new theories become available. The Iron Pillar of Delhi stands in the courtyard of the Quwwat-ul-Islam Mosque, surrounded by the ruins of a medieval Islamic complex that was itself built on the ruins of a Hindu temple. The pillar has outlasted them all. The temple is gone, the mosque is partially ruined. The rulers who built them and the rulers who destroyed them have been dead for centuries. But the pillar remains, its surface smooth and dark, its inscription still legible, its iron still sound after 1600 years of exposure to the elements. The pillar does not know that it is remarkable. It does not know that scientists have travelled from around the world to study its surface, to analyse its iron, and to understand the chemistry that has preserved it. It does not know that its survival has challenged the assumptions of modern metallurgy, inspired new approaches to corrosion protection, and demonstrated that the ancient Indian ironworkers produced a material that is, in one specific and critical respect, superior to the materials that the modern world produces. The pillar simply stands, as it has stood for 16 centuries, doing nothing more than existing, and in the act of existing, defying one of the most fundamental and most destructive processes in the natural world. The protective film on the pillar's surface is invisible to the naked eye. It is 1/20th of a millimeter thick, a layer so thin that it cannot be seen or felt, a layer that has been building itself, molecule by molecule, year by year, century by century, for 1600 years. The film is the product of a chemistry that the pillar's makers did not understand. A chemistry that involves the interaction of phosphorus, iron, oxygen, and water at the molecular level. A chemistry that produces a compound so stable, so adherent, and so impermeable that it has held the forces of corrosion at bay for longer than most civilizations have existed. The math is striking. 1600 years, 6.5 metric tons of iron, 1/20th of a millimeter of protective film, zero significant corrosion. The numbers tell a story that words cannot fully capture, a story of a material that has defied the fundamental chemistry of its own nature, that has resisted the process that destroys every other iron object in the world, and that has done so not through any human intervention, but through the silent, invisible, automatic chemistry of a natural protective film. The pillar is a message from the Gupta era, a message that was written in iron rather than in words, a message that says, "We could do this. We could produce iron of such quality and such purity that it would stand for millennia. We could forge a column of such size and such structural integrity that it would survive earthquakes, wars, and the passage of 16 centuries. We could create an object that would outlast our empire, outlast our religion, outlast our language, and that would still be standing, still intact, still defying the chemistry of corrosion, when a civilization that we could not have imagined finally came along and asked, how did they do it? The answer, when it came, was both simpler and more profound than anyone expected. The phosphorus in the ore, the smelting process that preserved the phosphorus in the iron, the climate of Delhi that promoted the formation of the protective film, the 1600 annual cycles of wetting and drying that built the film, layer by layer, year by year, into the thin, invisible shield that protects the iron from the atmosphere. The answer was not a secret formula or a lost technique. It was a convergence of natural conditions, a meeting of geology and chemistry and climate that produced a result that no one planned and that no one understood until the modern world brought its instruments and its theories to bear on the ancient metal. The pillar stands, the film protects, the iron endures, and the lesson of the Iron Pillar of Delhi, a lesson that has been 1600 years in the telling, is that the most enduring solutions are sometimes the ones that are not designed but discovered, not invented but inherited, not understood but simply, silently, and magnificently achieved. The pillar is older than most nations. It is older than most languages. It is older than the mosque that surrounds it, older than the empire that built the mosque, older than the religion of the empire that built the mosque. It has watched civilizations rise and fall around it, has seen rulers come and go, has witnessed the transformation of the world, from the ancient to the medieval to the modern, and it has endured through all of these changes, unchanged and unchanging, its iron as sound and as solid as the day it was forged. The inscription on the pillar, carved in the Brahmi script 16 centuries ago, is still legible. The letters are clear, their edges sharp and well-defined, unmarred by the pitting and the erosion that corrosion inflicts on unprotected iron. The inscription speaks of a king named Chandra, of military victories over enemies in the east and the west, of the erection of the pillar as a standard of the god Vishnu. The words are ancient, but they are preserved as clearly as if they had been carved yesterday, protected by the same invisible film that protects the iron from which they were carved. The traditions that produced the pillar are gone. The ironworking castes of ancient India, who possessed the knowledge of ore selection, of smelting technique, and of forging practice that was needed to produce iron of this quality, have largely disappeared, their knowledge lost to the economic and the social changes of the modern era. The specific ores that were used, the specific furnaces that were built, the specific techniques that were practiced are known to us only through the analysis of the iron that they produced, and through the observations of ethnographers who documented the last practitioners of the traditional craft. But the pillar remains, and the pillar, in its silent, enduring presence, tells us something that no written text, no oral tradition, and no modern experiment can fully convey, that the people who made it, working with simple tools and simple materials, guided by knowledge that was accumulated over millennia of practice and transmitted through generations of apprenticeship, produce something that the modern world, with all of its science and all of its technology, has not yet surpassed. The pillar is a testament to the power of empirical knowledge, to the value of accumulated experience, and to the extraordinary things that can be achieved when specific conditions converge in ways that no one planned and no one fully understood. The Iron Pillar of Delhi is a connection between the ancient and the modern worlds, a physical bridge that spans 16 centuries of human history and that links the metallurgical knowledge of the Gupta era to the materials science of the 21st century. The pillar was made by people who did not know the word corrosion and who had no concept of the electrochemistry of metal degradation. It was preserved by a chemical process that was not identified or understood until the late 20th century, and it was explained by a scientific tradition that did not exist when the pillar was made, and that has been developing for only a few centuries of the pillar's 1600-year existence. The pillar connects not only the ancient and the modern, but also the empirical and the theoretical, the practical and the scientific, the accidental and the deliberate. It was produced by an empirical tradition and explained by a theoretical tradition. It was preserved by an accidental chemistry and understood by a deliberate science. It stands at the intersection of all these oppositions, a reminder that the boundaries between them are not as fixed as we sometimes assume, and that the achievements of the empirical tradition can rival and sometimes exceed the achievements of the theoretical tradition. The Iron Pillar of Delhi will continue to stand, as it has stood for 16 centuries, its surface protected by the invisible film that chemistry has built and that time has perfected. The monsoon rains will fall, the summer heat will blaze, the Delhi atmosphere will carry its load of moisture and dust and pollution, and the pillar will endure, its iron unchanged, its inscription legible, its surface smooth and dark, a monument to a civilization that is gone, and to a knowledge that was accidentally achieved and accidentally preserved. The pillar does not boast. It does not claim credit for its survival. It simply stands, as it had stood since the time of the Guptas, doing what iron is not supposed to do, lasting. And in the act of lasting, it teaches us a lesson that is as relevant today as it was when the iron workers of the 4th century poured the last heat of their forge and shaped the last bloom of their phosphorus-rich iron into the column that would outlast their empire, their religion, their language, and everything else that they created, everything except the iron itself.